Every day, the Andromeda galaxy gets 300 million kilometers closer to us. That's like traveling the distance between Earth and the Sun twice a day. It's so big that even though it's 2.5 million light-years away, we can already see it with our naked eyes on dark nights. But let's imagine the impossible. Tomorrow morning, you wake up and Andromeda is right there, taking up half the sky, with its bright spiral arms slowly spinning above our heads. First would come the gravity waves, then the radiation storms, and then the most beautiful and terrible death dance in the universe would begin. Two supermassive black holes, each one millions of times heavier than our Sun, would start spinning around each other, creating waves in the very fabric of space and time. Is there any chance, no matter how small, that humanity could survive the biggest cosmic event possible? Subscribe to the channel, leave your like, and comment from what part of the world you're watching, because now I'm going to tell you everything. What would it even mean for Andromeda to collide tomorrow? The honest answer is that under normal physics it cannot, so the only way to talk about it is to set up a clean, deliberately artificial starting point and then let real laws take over from there. Start with the basics. Andromeda sits roughly 2.5 million light-years away, and the mutual orbit it shares with the Milky Way will naturally lead to a merger in about 4 to 5 billion years. That is the slow, stately picture backed by observations and gravity. If we say collide tomorrow, we are not pretending that it zooms here faster than light. Instead, we reframe the situation as a sudden rearrangement of the initial conditions. At a chosen moment, the mass of Andromeda is no longer far away but is placed nearby, and from that moment onward, we evolve the system with standard physics. This setup may sound like cheating, so it helps to say what it is not. We are not moving information or matter faster than light. We are not rewinding time or splicing timelines. In plain terms, we declare a new starting snapshot of the universe and then let it run. In technical language, it is a new state for the gravitational field and the matter in it, defined on a single moment in cosmic time. Once that state is set, everything afterward respects relativity, causality, and the usual conservation laws as they apply to the evolution that follows. The most convenient placement puts Andromeda's center a few tens of thousands of light-years from the Milky Way's center, roughly where the first closest approach would happen in a natural encounter. Close enough to matter immediately, but not so close that stars slam together, because star bodies are tiny compared to the distances between them. The disks would overlap in the sky, the halos would already be blended, and tidal forces would begin to reshape both galaxies from the first day. By choosing a location near first pericenter, which just means the point of closest approach in an orbit, we sidestep a long wait for light to travel and for gravity to build up from afar. In this starting snapshot, we carry over everything we know about both galaxies. Each has a massive dark matter halo, the invisible matter that outweighs the stars and gas and sets most of the gravity. The Milky Way's halo mass is thought to be around 1 trillion solar masses, give or take a factor of order 1, and Andromeda's is similar or a bit larger. Both galaxies have stellar disks with bars and spiral structure, thick components of older stars, and gas that orbits, collapses into clouds, and forms new stars. We preserve those properties. What we change is the separation and the relative motion. We give the pair a relative speed of a few hundred kilometers per second, aimed so that they are passing their first near miss, not head-on at zero impact parameter. That way, the scenario matches the paths astronomers simulate when they reproduce galaxy collisions. Does this violate energy or momentum? It would, if we cared about the one jump that moved the galaxy. Since the jump is only a thought tool, we keep our bookkeeping from the moment after the placement. At that moment, the galaxies have well-defined masses, positions, and velocities. The total energy of the pair can be set to a bound orbit, which means the combined pull of gravity is strong enough to keep them dancing until friction-like processes gradually bring them together. That friction is not the everyday kind with rubbing surfaces. In galactic dynamics, it refers to gravitational tugs between massive clumps and the sea of smaller bodies around them, a process called dynamical friction. It drains orbital energy into random motions of stars and dark matter, slowly shrinking the orbit. Another choice we must make is which version of Andromeda we bring close. Because light takes time to travel, the Andromeda we normally see is the one from about 2.5 million years in the past. If we want a clean comparison, we pick the Andromeda that exists right now in the same cosmic time as us, with the same star ages, the same gas content, and the same central black hole activity it has today. That avoids paradoxes about seeing different epochs of the same object. It also means that the photons that used to be streaming from Andromeda toward us out in intergalactic space are suddenly irrelevant. The local sky would now be dominated by the light from a galaxy that is actually nearby, not by an echo from long ago. With the mass distribution reset, the local gravitational field is simply the one produced by two overlapping halos and two interleaved stellar disks. There is no signal to wait for because we are not watching it change. We are starting from the changed state. From that moment, stars in both galaxies respond to a deeper combined potential. Potential here just means the landscape of gravity that tells objects which way to accelerate. Near the solar neighborhood, the force would not flip overnight, but the background tug would be subtly different, nudging orbits and setting up slow waves in the disk. Farther out, where the halos blend strongly, those waves would be more dramatic, setting the geometry matters as well. The two disks are not aligned in real life, and keeping that misalignment makes the thought experiment more honest. Andromeda's disk would arrive tilted relative to ours, with its own spin axis and bar pointing in some direction on the sky. The relative motion would have a sideways component so the galaxies do not slam together face on. That sideways component carries angular momentum, which is the measure of how much spin is in the encounter. High angular momentum favors long tidal tails and bridges. Low angular momentum favors a quicker, more direct plunge. For a tomorrow scenario that is interesting but not instantly destructive, a moderate angular momentum passage near first pericenter is a natural choice. We also need to be clear about the word collide. Galaxies are mostly empty space by volume, so stars rarely hit each other. A galactic collision is mainly a gravitational event, with the orbits of stars and dark matter being deflected, and a gaseous event, with clouds of gas actually ramming into one another and producing shocks. The thought experiment preserves that distinction. By moving Andromeda close, we are not conjuring a fireball. We are setting the stage for gravity to stir the disks and for gas to start compressing wherever the flows intersect. That is the right physical picture used in computer simulations of mergers and in interpretations of real interacting systems we see across the sky. People always ask what happens right away. With the setup above, the overnight change is almost entirely visual. The sky would showcase a vast, detailed swath of dust lanes and star clouds, yet the total light spread across the sky would be faint enough not to erase the day. Gravity works on orbits over long times compared to a human day, so the mechanical effects are modest at first. That is a feature of the framing, not a dodge. It makes the scenario something we can analyze patiently, with telescopes and with models, without pretending that apocalyptic physics ignores the scales involved. There are other ways to pose the thought experiment, and it is worth saying why they are less useful. You could imagine Andromeda popping into existence right on top of the Milky Way's center with zero relative motion. That would be an unrealistically violent case, more like building a single galaxy by hand than watching two galaxies interact. You could also imagine it appearing far out beyond the halos, leaving us to wait millions of years for the first real effects, which defeats the point of asking about tomorrow. The middle ground, near first pericenter with a sensible sideways speed and a tilted orientation, keeps the physics rich while still giving immediate observable changes. Finally, it helps to think about how scientists would know that this is a physically consistent setup rather than a fantasy dressed as science. The telltales would be the same ones used when interpreting real mergers. The shapes of tidal features would trace the recent path and angular momentum. The speeds of stars, measured by precise astrometry, would show coherent streaming motions caused by the combined potential. Gas would reveal sharp boundaries where flows meet. If all of those signatures line up with a near pericenter passage, then the framing is doing its job. It gives a starting point that is contrived in how it appears, yet entirely governed by ordinary gravity, radiation, and plasma behavior once it begins. With that scaffold in place, talking about what unfolds makes sense. A nearby Andromeda from day one, governed by rules from then on. Given that nearby starting point, the very first day is mostly about what the sky looks like and what instruments pick up, because gravity will still be working on humanly slow timescales. The change you would notice is visual first, and it would be unmistakable the moment the sky gets dark. A vast arc would appear, running across a huge span of the sky, textured with dark dust lanes, scattered bright knots, and broad, uneven patches of light. It would not turn night into day. The light is spread thinly over a large area, so the total brightness to your eyes would remain gentle. But the detail would be far beyond what we are used to seeing with the naked eye. You would be able to make out mottled patterns and curved bands with no optical aid at all, especially from dark, clear locations. During daylight, the sun will still dominate. The sky would look the same as any normal day because the scattered sunlight in the atmosphere overwhelms faint extended glows. If you looked for Andromeda's structure at noon with a telescope, you still would not catch it, for the same reason you cannot see the Milky Way in daylight. Once twilight fades, the picture changes. Even in towns with some lighting, you would notice a pale arch rising and falling as the Earth rotates. In truly dark countryside or mountain skies, you would see rich texture. Dark, thread-like dust lanes cutting across brighter sweeps, and a curvature that gives away the spiral pattern of Andromeda's disk as it overlaps our own. Human eyes are poor at seeing color in dim light, so most people would describe it as grayish or slightly bluish. Cameras tell a different story. With a handheld phone and an exposure of around 10 seconds, you would record deep blues from clusters of hot young stars and soft reds from wide hydrogen clouds lit by newborn stars. With a small amateur telescope and a modest camera, you could stack a few short exposures and tease out the beaded look of star-forming regions strung along spiral arms. The darker dust lanes would stand out crisply as jagged gaps where starlight is blocked. Because the two disks are misaligned, you would notice an interplay between our Milky Way band and the newcomer's structure. The familiar Milky Way would still run as a bright river of stars across the sky, but Andromeda's broader disk would cut across it at an angle. Where they overlap, dust in either galaxy would veil parts of the other, creating complex silhouettes. In some sections, you would see layered structures, our nearby star clouds in the foreground, then a thinner veil of dust, and behind that the luminous swath of Andromeda's stars. This layering would not be smooth. It would vary across the sky, giving you a sense of depth even with normal eyesight. No shadows would be cast by this glow, and street lighting would still drown much of the faintest detail in cities. Dark sky locations would become prized overnight because the view there would be arresting. Observatories and amateur astronomers would begin systematic imaging immediately. Wide-field images taken in the first hours would already show hints of tidal features, faint, elongated strands of stars reaching between the disks. Those are the earliest footprints of tidal forces pulling stars outward along curved paths. They would be dim, but sensitive cameras and long exposures would catch them. If you try to see them with your eyes, you would probably not, because the surface brightness is low, but patient imaging would reveal them quickly, spectroscopically, which just means splitting the light into its component colors to measure velocities. We would get a burst of new information right away. The shifted wavelengths of spectral lines across different parts of Andromeda's disk would map its rotation, but now at a scale spread across the whole sky. We could watch how different sections are moving toward or away from us with a precision already routine in modern astronomy. That would confirm the relative motion set by the starting conditions and show if any initial shocks in the gas are forming where the flows from the two disks intersect. You would not notice any of this by eye, but astronomers would be able to publish velocity maps within hours using spectrographs on mid-sized telescopes. Radio observatories would go full throttle immediately. Neutral hydrogen emits at a characteristic radio wavelength, and that line is a workhorse for mapping gas in galaxies. On the first night, arrays would begin scanning for changes in the hydrogen distribution and for broadened or multiple components that indicate overlapping gas streams. Because radio waves pass through dust, these maps would fill in the regions where optical light is obscured. We would expect to see sharp gradients in velocity where the two gas layers start to meet. Those are the places where shocks will form. The shocks will not be huge explosions. They are more like traffic jams in gas flows, compressing and heating the gas. Early signs might include faint diffuse radio continuum emission from electrons being accelerated in turbulent magnetic fields, building gradually over days and weeks. The first 24 hours would already show firm evidence that gas is beginning to interact. Infrared telescopes would trace dust warmed by starlight. In the first day, the infrared sky would look busy but not yet fundamentally changed in total output. The most striking differences would be spatial. Large structures of dust would be lit from new angles, and long, cold filaments would show up where we have not seen them before simply because they have been too far away. As gas compresses along the meeting zones, dusty ridges would brighten modestly. That infrared glow helps astronomers estimate where star formation is about to light up. Most brand new stars will not appear within one day. Forming stars takes at least hundreds of thousands of years, but the material that will become those stars would already be gathering, and the patterns would be visible. In the ultraviolet and X-ray range, satellites would search for hotspots. The first day would deliver delicate signals, edges where gas is heated as it is squeezed, and compact sources in the cores of both galaxies if their central black holes begin to wake up slightly from an increased supply of falling gas. A dramatic active phase for a black hole is not a one-day process. It builds as gas loses angular momentum and trickles inward. Still, small flares and changes in hardness of the X-ray spectrum would be measurable, indicating that the environment around the centers is growing denser and more dynamic. Gamma-ray observatories would mostly keep watch for individual transients like gamma-ray bursts or flares from known sources. The background would not spike immediately just because the galaxies are near. It is the cumulative result of many events over long periods. Back to what you can see with your own eyes, the apparent size would be staggering. The structure would span a huge fraction of the sky, far larger than any familiar object. Because we set the initial condition near first closest approach, the disks would already overlap in projection. That means a person in either hemisphere could go outside, look up on a clear night, and find substantial sections of the newcomer's disk crossing overhead at some point during the Earth's rotation. The exact path would depend on your latitude and the orientation of the encounter, but it would be so extensive that almost everyone would have a clear view daily, weather permitting. If you point binoculars toward the arcing light, you would see star clouds become granular like coarse sand rather than a smooth smear. You would pick out compact clusters as tiny, sharp beads, and in front of them, the dark filaments would look like cigarette smoke frozen into place, snaking across the glow. With a small telescope, you would resolve fresh details, tiny glowing patches where hydrogen is being ionized by hot young stars, and bluish clusters that mark recently formed stellar associations. The term association here just means a loose group of stars born together. In long exposure images, faint bridges of stars would trace graceful curves between the two disks, evidence that gravity is already redistributing angular momentum and pulling material outward. People might worry about immediate mechanical effects on Earth, like new tides or sudden shifts in the night sky star patterns. The truth is that in one day, those are negligible. The global tides in our oceans are dominated by the moon and the sun. The change in the large-scale gravitational field from a shifted galaxy is spread so smoothly over such a vast region that it does not create strong gradients at the scale of our planet. You would not see the constellations jerk or drift. The tiny changes in star positions would require years of careful measurement to notice. What you would see are new backdrops and features that are extended and diffuse, not pinpoint changes in the familiar stars. On instruments measuring stellar motions, the first day would open the door to a new kind of astrometry. Astrometry is just precise tracking of positions and motions on the sky. Space missions already operating could start gathering micro-changes in proper motions, the sideways drift of stars over time. No catalog would show dramatic jumps in 24 hours, but astronomers would immediately set up differential measurements, comparing precise positions taken that night to earlier ones to begin tracking any coherent flows caused by the deepened gravitational potential. The first day is about setting baselines because the story of motion takes time to unfold. The airglow and weather on Earth would still control how much you can see from the ground. Even under a stunning galactic panorama, clouds are clouds and haze is haze. When the weather cooperates, the scene would be the most extraordinary nocturnal vista humans have known, and it would be consistent from night to night with only slow evolution. Photographers would rapidly build mosaics that wrap around the sky, stitching together panels to capture the full structure. Planetariums would rush to update their projectors with real images instead of simulated textures. Kids looking up from cities would still have to fight light pollution, but outreach groups would move telescopes and cameras to schools and parks, because even a few seconds of exposure on a small sensor would show the structure crisply. One subtle visual effect would stand out to careful observers. As the Earth rotates, the brightest patches and dust lanes would appear to move relative to the horizon, and the perspective would make some sections look taller or more inclined at different times of night. This is just geometry. The underlying structure is larger than we are used to, so our rotation presents it at constantly shifting angles. The view would also change gently with the seasons because the night side of Earth faces different parts of the sky as we go around the sun. All of that would be predictable and trackable with simple sky charts updated for the new features. The first day would also give us immediate color composites across wavelengths from professional teams. Radio images would be mapped to reds or blues, infrared to softer tones, optical to natural colors, ultraviolet and X-ray to false colors that highlight energetic processes. When you see those, remember that they are translations of data outside human vision into a form we can apprehend. In reality, your eyes will be most sensitive to the optical band, and the scene there will be dominated by starlight and dust shadows. The fine points about shock diagnostics or velocity dispersion maps will live on screens and in papers, not in the naked eye experience. There is a small but interesting point about light that was already en route to us before the shift. Photons that left Andromeda millions of years ago are still traveling through intergalactic space, but they no longer matter observationally because we now have the galaxy itself nearby supplying light that reaches us almost immediately. No one would notice a jump because our detectors and eyes respond to what arrives at each moment. The practical outcome is that astronomers would retire the old, faraway view and replace it with a local, much brighter and more detailed view right away. If you worry about spaceflight and satellites, nothing would break on day one. Star trackers on spacecraft that use star patterns to orient themselves would still recognize their catalogs because the individual bright stars that those systems use remain in their same places to within the precision needed. The extended light from the nearby disk might slightly increase background levels in some directions, but that is manageable with software thresholds. Ground-based telescopes would make new flat-field calibrations to account for the extra diffuse light in wide fields, just as they do for the Milky Way background now. The public reaction would be intense curiosity. Scientists would set up live feeds of the sky from different latitudes. You would see how the arc looks from the southern hemisphere compared to the northern hemisphere, and how the Milky Way's band braids with the new structures. Observatory schedules would be torn up and rewritten to prioritize continuous monitoring in radio, infrared, optical, ultraviolet, and X-rays. Data would pour in and be shared quickly because, although the first day is visually stable, the chance to set baselines and catch the earliest moments of gas interaction is precious. By the end of the first 24 hours, the consensus would be clear. The immediate change is overwhelmingly aesthetic and scientific. The sky is transformed into a high-resolution panorama of another galaxy's disk laid across our own, full of fine structure and subtle gradients. Instruments register the first signs of gas starting to squeeze where flows meet, and spectrographs map velocity patterns that confirm the geometry and motion of the encounter. Nothing catastrophic happens to the Earth, the oceans, or the constellations. The most urgent task is to observe, catalog, and understand, building the time series that will let us track how this new configuration evolves from night to night and year to year. The scene is set, the lights are on, and the first day gives us the closest look humanity has ever had at the inner workings of a galactic neighbor. With that new skyline locked in and instruments already building their first maps, the next layer is what gravity is doing behind the scenes to the big structures that make up both galaxies. The short version is that the unseen mass envelopes, the dark matter halos, meet first and set the tone for everything else. A halo is a vast, roughly spherical cloud of invisible matter that outweighs the stars and gas. It extends far beyond the visible disk, and because it is made of particles that barely interact except through gravity, it passes through another halo without rubbing but not without effect. When two halos overlap, the combined gravitational pull grows deeper and more lopsided, and that distorted pull starts to stretch, twist, and thicken the stellar disks that live inside. Right away, the deepened potential shifts orbits from the clean, nearly circular paths they had when each galaxy was on its own. Think of the disk stars as a crowded freeway of objects circling in the same general direction. Add a nearby massive companion, and the directions of those lanes are no longer perfectly concentric. The overall pull is not symmetric. That asymmetry creates tides. A tide in this context is just a difference in gravitational pull from one side of a region to the other, and it is those differences that do the work of rearranging orbits. The outer parts of the disks are the most responsive because the stars there are more lightly bound. You start to get long, faint extensions drawn out from the edges and curved structures that bridge between the galaxies. Those are the tidal tails and bridges that observers will photograph in the coming nights and weeks, and they are gravity's way of moving angular momentum outward. Angular momentum is the bookkeeping for spin. In a merger, it does not vanish, it moves around. Tidal forces torque the disks, pumping angular momentum into the outskirts and, to some extent, into the halos. The inner regions can lose some of that spin support and become more elongated. In many simulations of encounters like this, bars grow quickly in the inner disk. A bar is an elongated arrangement of stars across the center, not a solid object, but a pattern. It forms because the non-circular pull of the companion lines up orbits in a way that reinforces a stretched shape. Once a bar forms, it tends to drive further changes. It can shuffle stars inward and outward through resonances, and it can shepherd gas, though the gas part is better handled when we talk about shocks and starbursts. There is also the question of how the two disks are tilted relative to each other. Misalignment matters. If the planes are not parallel, the tide has a vertical component that lifts parts of a disk above and below its original plane. That sets up a warp. A warp is a gentle bending of the disk, not a break. You can picture the outer ring of the disk twisted like the brim of a hat. This bending travels as waves through the disk, called bending waves by dynamical folk, and they propagate at speeds tied to how stiff the disk is, which depends on how quickly stars oscillate vertically and how dense the disk is. Over time, this vertical stirring also heats the disk. Heating, in dynamics, means more random motion. Stars that once followed thin, cool, nearly circular paths gain vertical and radial motions, and the disk puffs up into a thicker layer. Everyone always asks about timescales, and here is the careful way to say it without getting ahead of ourselves. The large, graceful structures like tails and bridges become obvious over spans of many tens to hundreds of millions of years. But the seeds of them are sown now. The halo overlap is immediate in our setup, so the torques begin immediately. You will not watch a tail grow in a week, but you will see the kinematic signatures, the speed patterns, that signal where they are forming. In the inner disk, changes can show up sooner as patterns because orbits there are faster. Bars can strengthen on the scale of a few galactic rotations, which for inner regions means far less than 1 billion years. Another key player is dynamical friction. Despite the name, nothing is scraping. This is a gravitational drag that affects massive bodies moving through a sea of lighter particles. The moving mass, which could be a galaxy's bulge, a bar, or even the whole companion galaxy, pulls on nearby stars and dark matter and leaves behind an overdense wake. That wake pulls back on the mover, robbing it of orbital energy and angular momentum. The result is that after this first close passage, the separation gradually shrinks. Each subsequent passage will bring the galaxies closer until they finally coalesce. The efficiency of this process depends on the mass distribution and on how much substructure the halos carry, because clumps and satellites amplify the wake. You might hear astronomers talk about resonances during encounters. A resonance is a simple numerical relationship between the rates at which a star goes around the center, wobbles radially, and, in a bar's presence, sees the pattern sweeping by. When those rates line up, stars exchange angular momentum with the pattern efficiently. The inner Lindblad resonance, which is a common one in barred galaxies, tends to collect stars into ring-like features near the inner parts. The outer Lindblad resonance can do something similar farther out. These are not arcane details. In real images of interacting galaxies, ring structures are common, and their radii are set by exactly these resonant conditions. In our case, as the bar grows and slows, those resonance radii move, and stars and gas get shepherded into changing rings and arcs. The gas story includes shocks and star formation. For the stars, the effect is clean redistribution. A different kind of asymmetry, a lopsided pattern, often grows too. Instead of a two-armed symmetry like a classical spiral, the disk can become one-sided for a while with more mass on one half than the other relative to the center. This one-armed, or M=1 mode, comes from off-center forcing by the companion and from the response of a live, responsive halo. It displaces the center of mass of the visible disk relative to the center of the dark halo. Observationally, you would measure this as a twist in the velocity field and as an off-center appearance of the inner isophotes, which are contours of equal brightness. The mode can persist for many rotations, and it is a very effective way to shuffle stars and to heat the disk. The combined halos do more than tug on the disks. They exchange energy and angular momentum with each other. Think of a stream of dark matter particles from one halo flying through the other halo and being deflected. Those deflections add up statistically to a transfer of momentum. Over time, the halos become more merged, sharing a common envelope that wraps both stellar systems. When that happens, the outermost tidal tails find it harder to escape because the deeper shared potential keeps them bound. Some of the material launched into a tail will later fall back, arcing over in long trajectories that can splash back into the remnant and build shells or loops. Those are faint signatures that observers love because they trace the history of the orbit and the mass distribution. Closer in, the bar and spiral patterns draw energy from the organized rotation and put it into random motions. In the language of disk dynamics, stars gain velocity dispersion. That simply means they wobble more, inward and outward, and up and down. In a quiet disk like the Milky Way today, the thin disk has relatively low dispersion. Stars move almost together. During an encounter, the dispersion grows. That thickens the disk and reduces the clarity of spiral structure. Once the velocity dispersion is high, spirals have a harder time staying coherent. The end state of repeated passages is a system where orbits are mostly random, which is why massive mergers often end up as more rounded, less disky galaxies. That is the long arc of the process. The first steps of it begin as soon as the non-circular forces arrive. Orientation also matters for how spirals respond. If the encounter is prograde, meaning the companion moves in the same rotational sense as the disk it is disturbing, spiral arms can be amplified strongly. The arm segments line up with the forcing and get stretched into long, graceful patterns. If the encounter is retrograde, with opposite sense, the response can be weaker in terms of visible spirals, but stronger in terms of heating. In our contrived initial condition, we picked a configuration near first pericenter with a reasonable sideways speed and a tilt, which gives a mix of both effects. The Milky Way's existing bar would feel a strong torque that could either strengthen it or, depending on phase, briefly weaken it as orbits are shuffled. Over time, bars tend to grow in mass and slow in rotation during interactions because they transfer angular momentum outward and feel dynamical friction with the halo. It is worth touching on the role of satellites and subhalos, the smaller companions that both big galaxies carry. These substructures get stirred up during a major encounter and can be redirected onto new orbits that sweep through the disks. Each one is a little gravity hammer, heating the disk along its path, kicking stars slightly and adding to the overall thickening. They also contribute to the dynamical friction background that drags on the big centers. Some satellite galaxies may be pulled into tidal tails, stretched into streams that drape the sky. Those streams will be among the easiest things for wide-field cameras to detect in the coming years of this scenario, and they give sharp constraints on the mass and shape of the combined halo because the streams trace the potential like test particles. From the perspective of observers making velocity maps, one of the first measurable consequences will be departures from a clean, flat rotation curve. In an isolated disk, the speed of rotation as a function of radius tends to flatten beyond the inner region because the dark matter halo provides most of the pull. During an interaction, non-circular motions become significant. Along some lines of sight, stars and gas move faster than circular on the near side of a tidal arm and slower on the far side. Spectra pick that up as skewed or split-line profiles, and mapping those across the sky reveals the flow patterns. For stars, the changes are subtle at first. For gas, the signals are sharper because gas responds more coherently to pressure and shocks. But again, the gas collisions are a story in their own right. Radial migration is another quiet but important effect. That phrase describes stars changing their average orbital radius without becoming much more eccentric. It happens when stars linger near corrotation, the radius where a pattern like a bar or spiral rotates at the same angular speed as the stars. In that situation, small torques can move stars inward or outward by several thousand light-years over long times without heating them as much. An interaction loads the disk with strong patterns, so migration can proceed rapidly compared to a quiescent phase. One outcome is that the chemical gradient of the disk, the way heavy element abundance changes with radius, gets blurred. Stars born in the inner, more enriched regions wander outward, and vice versa. That blending shows up later in the spread of ages and compositions that surveys would map. As the bars and spirals rearrange matter, the central regions react strongly. A bar tends to funnel mass toward the inner kiloparsec scale, raising the central density. That does not mean a sudden collapse or a black hole feeding frenzy on day one. It means that orbits inside the bar change shape in a way that lets material lose angular momentum and move inward. The dark matter halo reacts too, slightly contracting near the center in response to the increased baryonic pull, a process often called adiabatic contraction. In some cases, feedback from central activity can later puff that back out, but the purely gravitational step is inward mass flow. The centers also become triaxial, which means not round in any cross-section, and that three-dimensional shape changes the precession of orbits, opening more routes for stars to exchange energy and angular momentum. Vertical oscillations, the up and down motion of stars through the midplane, get coupled by the encounter into large-scale bending modes. You may have heard of corrugations in the Milky Way's outer disk today, gentle ripples where star counts rise and fall across the plane. An interaction enhances that kind of structure. Parts of the disk are pulled up, other parts pushed down, and as those waves travel, they interfere to make a complex pattern that evolves slowly. The net effect again is to puff the disk and to break the clean symmetry about the plane. Over time, some stars are scattered onto halo-like orbits, forming a thicker, rounder component that surrounds what is left of the thin disk. All of these processes occur in both galaxies, but not identically. Andromeda's disk is larger and likely more massive than the Milky Way's, and its central black hole is more massive too, though that belongs to the black hole discussion elsewhere. Mass matters because the more massive galaxy exerts stronger tides and also resists being disturbed a bit better in its inner regions. The outcome is asymmetric. One disk may throw a longer, more prominent tail, while the other shows a stronger bar or warp. Observers will take advantage of those differences to infer the mass ratio and the orientation of the encounter. The details in the shapes of the tails and the timing of when rings and bars appear act like fingerprints, telling us which galaxy took which role. Uncertainties remain, and being honest about them helps set expectations. The total masses of the halos are known only within broad ranges, and the exact distribution of mass with radius is still debated. Those uncertainties translate into a spread of possible strengths for the tides and the friction. The amount and clumpiness of gas change the response of the disk patterns and the central mass flow, because gas can dissipate energy. Even the presence of a pre-existing bar, as the Milky Way likely has, sets initial conditions that can amplify or delay certain features. That is why telescopes will be busy measuring the actual velocity fields and structures rather than relying on a single simulation. From our local vantage, if you live within the disk of the Milky Way, the gravitational dynamics will not feel like a shove. They accumulate quietly. The Sun and nearby stars orbit within a region where the local mass dominates the force you feel, and the tides from the combined halo act gently with long periods. What you could detect with precise measurements are streaming motions, small systematic flows superimposed on the dominant rotation, and a slow increase in random velocities. The big visible consequences live on the sky at large scales, the arcs and bridges and warps that lay out the choreography of the encounter. Piece by piece, gravity in overlapping halos and distorted disks takes a clean spiral pattern and complicates it. Tails lift stars far from their birthplaces. Bars line up orbits and redistribute angular momentum. Warps and bending waves upset the neat mid-plane symmetry. Dynamical friction tugs the big bodies onto tighter paths. Resonances mark out rings and lanes where stars linger. There is no need to invoke exotic physics. The familiar rules of gravity and orbital motion, applied to a very large and lumpy system, do all of this. The first day gives us a snapshot at the start of this evolution, and from there the slow remodeling of both galaxies proceeds as tides, torques, and wakes do their steady work. All that large-scale stirring is the backdrop, but what most people want to know is what it means for the Sun and the planets. The short answer is that over human timescales, the solar system keeps doing what it has been doing, and the risks that do grow are statistical and delayed, not sudden jolts. The way to keep this clear is to separate the immediate gravitational environment that holds the planets together from the much broader field that is reshaping the galaxies. Right now, and for a very long time, the Sun's gravity rules everything out to the far edge of the Oort cloud. The extra pull from a neighboring galactic disk that has been dropped nearby is widespread and smooth. So across the scale of a few dozen astronomical units, which covers the planets, it barely changes the force balance. Astronomical unit just means the Earth-Sun distance. The gradient of the galactic field across that span is tiny compared to the Sun's grip. That means Earth stays on its path, the gas giants keep their resonances, and the fine structure of the inner solar system is unaffected in any day, year, or even in many lifetimes. Tides in our oceans still come from the Moon and the Sun. There is no new galaxy tide that you would notice as a rise in sea level or a shift in day length. Where the story begins to pick up is on the scale of the Sun's orbit around the Milky Way and the cloud of icy bodies that surround the planets at enormous distances. The Sun goes around the galactic center roughly once every few 100 million years on what is, at the moment, a modestly eccentric, gently inclined path through the thin disk. With the combined halo of two big galaxies now overlapping, the net gravitational potential around us is a little deeper and not quite as symmetric. Over time, that sows small changes into the Sun's path. Random motions grow. The vertical bounce of the Sun above and below the midplane increases, and the sideways orbital speed picks up a bit of scatter. That is called dynamical heating, and it is the same process that puffs up the stellar disks overall. In practical terms, imagine the Sun's once crisp, nearly circular orbit turning into a slightly more eccentric loop and gaining a taller bobbing motion out of the plane. Nothing abrupt. Over tens to hundreds of millions of years, the Sun could drift a few thousand light-years inward or outward through a process called radial migration. That happens when the Sun's orbit interacts with long-lived patterns like a bar or spiral at special locations called corrotation, where the pattern and the Sun circle at similar rates. The torques there are efficient at moving orbits without making them wildly elongated. A migration outward is quite plausible in a merger because angular momentum is moving to the outskirts. If that happens, the Sun ends up in a less dense region of the eventual remnant, which actually improves long-term stability. What about being grabbed by Andromeda specifically rather than the Milky Way? Once the halos overlap and the pair begin dancing around their common center, the old labels lose some meaning. If the Sun's guiding center shifts toward the side associated with Andromeda's disk, you could say it has been captured in a loose sense, but there is no sharp line. The Sun orbits inside a shared envelope, and over repeated passages it will respond to the whole potential, not to one disk alone. If you want a crisp outcome in everyday language, the Sun is likely to end up orbiting far from the center of the merged system, probably on a more elongated, puffed-up path than it has today, but still bound. The most concrete risks are not from the smooth background. They come from chance flybys of other stars and from crossings of denser clouds. The merger stirs everything. It raises stellar densities in some regions, increases the range of stellar velocities, and redirects some satellite systems inward. That combination nudges the odds of close encounters upward. A close encounter here does not mean a collision. It means another star wandering within a few thousand to a few tens of thousands of astronomical units of the Sun. Encounters at that distance tug at the far outer Oort cloud, the reservoir of comets that live loosely bound to the Sun on orbits that can be as big as a couple of light-years across. A pass within a few tens of thousands of astronomical units is enough to jostle a lot of comets. Some get pushed inward along long, slow ellipses that eventually dip into the inner solar system after hundreds of thousands to millions of years. Others are nudged just enough to escape and drift as interstellar objects. We already have one famous example on the books in our unperturbed future. A small star called Gliese 710 is expected to come within roughly 20,000 astronomical units in about 1.5 million years. In a merger environment, you would expect the frequency of that class of encounter to increase, not everywhere and not instantly, but more often in stirred-up neighborhoods and during phases when the Sun crosses denser parts of the disk or its warp. The immediate consequence of such a flyby is not an instant hail of comets. The delay is the key. The comets that are nudged onto sunward paths still have to fall a long way, and that takes time. When they arrive, the impact risk at Earth does rise above the background. How much depends on how many were injected and on the architecture of the planets, which can deflect or eject a portion of them. Past studies of comet showers suggest that the inner planets can see an elevated impact rate over stretches of hundreds of thousands of years following a strong Oort cloud disturbance. That would be a real biospheric hazard, but not an every-century crisis. It is a long-tail risk that comes in slow waves. For planetary orbits themselves, the thresholds for real trouble are much tighter. To significantly torque the orbits of the outer planets, a star would need to pass within a few hundred astronomical units. To make inner planetary orbits like Earth's change in major ways, you are talking about even closer distances. Those are rare even in a crowded disk. In a typical Milky Way environment, the chance of a star passing within a few hundred astronomical units during the Sun's main sequence lifetime is very small. A merger lifts that probability, but it does not make it likely. The overwhelming majority of stars go through major interactions without any one star threading that tiny needle. There is a different class of perturber that matters. Giant molecular clouds. These are cold, dense blobs of gas and dust with masses of hundreds of thousands to millions of suns. They are not point masses, so their tidal influence spreads out, but when the Sun crosses near one, the cumulative pull across the Oort cloud can be significant. Encounters with clouds are part of the normal galactic weather even today. During a merger, more gas is driven into spiral ridges and bars, and cloud complexes can be more massive and more numerous along particular lanes. That means the odds of a stronger than average cloud tide rise, especially if the Sun's orbit carries it through those lanes. Again, the likely outcome is an increased trickle or burst of comets over geologic times, rather than a sudden mechanical change to the planets. You will hear dramatic phrases like ejection into intergalactic space, and that can happen to some stars in mergers, but the mechanism and the odds matter. To throw the Sun completely free, you need to boost its speed above the escape speed of the combined system. That is several hundred kilometers per second at least, and more likely closer to 1,000 depending on the final mass of the merged halo. The cleanest way to get that much energy is a slingshot off a hard, compact gravitating pair, like the binary of the two supermassive black holes once they have sunk to the center and hardened. That interaction requires the Sun to pass within a tiny central volume near the galactic core, which is not a place it is likely to visit. Other ways, like a very close encounter with a massive star cluster or a compact satellite galaxy, can give a kick, but getting all the way to escape is rare. Far more common is partial heating that sends the star onto a higher, more eccentric orbit within the halo. A softer outcome, still interesting, is that the Sun could be tossed out into a tidal tail. Tails are long, low-density streams of stars flung out by gravitational torques. If the Sun ends up in one, the local environment gets quieter in some ways, star density declines, and the rate of close encounters goes down. The flip side is that you spend a long time far from dense, star-forming gas, which is fine for stability but changes the long-term cosmic scenery. From a life and habitability point of view, a tail is not a bad neighborhood. The biggest consequence is simply distance. You are far from the action, which makes the sky dimmer when it comes to bright star-forming knots and supernovae. Closer to home, the Kuiper Belt and the inner Oort cloud sit in the zone where close stellar flybys begin to matter. The Kuiper Belt, out to a few dozen astronomical units, is shielded pretty well unless a star comes within a few hundred astronomical units. That is unlikely even with elevated encounter rates. The inner Oort cloud at a few thousand astronomical units is more vulnerable. A pass within that range changes the population noticeably, pumping some bodies inward. The architecture of the giant planets then shapes what happens next. Jupiter and Saturn are efficient at ejecting a fraction of long-period comets back into interstellar space, which is why the Earth does not face an overwhelming storm even when the injection rate rises. But there is a residual that gets through, and that is the piece that matters for impact risk. The solar system's slow drift through the evolving gravitational field also changes what kinds of stellar populations it meets. Today, our neighborhood is dominated by relatively old, low-mass stars. During a merger, the overall distribution gets stirred, and the Sun may cross regions where there are more massive young stars, more binaries, and more remnants like white dwarfs and neutron stars. Binaries are notable because a binary passing by can have a stronger tidal effect than a single star of the same total mass if the geometry lines up, since the two components tug in slightly different directions across the scale of the Oort cloud. The probability of a binary coming within the key distances is still small, but in an elevated density environment, it is another source of extra kicks. Even as these external influences tick up, the intrinsic stability of the planetary system is strong. The major resonances among the planets that have kept the inner solar system relatively calm for billions of years do not unravel because of a faraway galactic encounter. Numerical studies that throw random passing stars at solar system analogues show that you need very close approaches to see anything dramatic happen to planetary eccentricities and inclinations. Most of the time, you might get minute changes in Neptune's orbit or tiny shifts in the precession rates of the inner planets, far smaller than the fluctuations they already experience from their mutual pulls and from the Sun's oblateness. One subtle effect that will be of interest to planetary scientists is the way the changing galactic tide modulates the orientation of the Oort cloud. The cloud is not a perfect sphere. The slow tug of the galaxy stretches it into a slightly squashed shape and sets a preferred plane for the aphelia of the comets, which is the point farthest from the Sun on their orbits. As the large-scale field gets lopsided and then slowly reorients through the stages of the merger, that preferred plane will drift. Over many millions of years, that changes which parts of the sky long-period comets tend to come from, and it can make comet showers arrive in clusters linked to the Sun's phase in its vertical oscillation. That is not something anyone would notice day to day, but over geological times it leaves a pattern in the cratering record. On the question of capture by one disk or the other before full coalescence, there is a simple practical answer. If the Sun's guiding center moves toward the Andromeda side after a close passage, the local star field will gradually look more like Andromeda's population in terms of average star ages and kinematics. The solar orbit will then be described best by an orbit around the pair's common center, at a radius where the Andromeda disk contributes more to the nearby gravitational field. That feels like capture, but again, no sharp boundary is crossed. What you will see are different mix of nearby stellar types, slightly different average velocities, and, over very long times, a migration onto orbits that feel the eventual remnant's smooth, rounder potential rather than today's thin disk. There is also the long-tail possibility that the Sun, after being scattered outward, ends up on a very loosely bound orbit that carries it far into the outer halo for billions of years. Out there, the background radiation field is lower, the rate of nearby supernovae is lower, and the sky is sparse. The downside is fewer close star-forming regions to light up the sky. From a survival standpoint, it is a quiet, uneventful place. If instead the Sun remains in the thickened disk, the environment stays more familiar, with occasional passages through spiral density ridges and a higher long-term chance of mild perturbations from stars and clouds. Neither path spells doom. They describe different flavors of galactic weather. It is important to be frank about uncertainty. The exact odds for close stellar flybys depend on where the Sun ends up after the first passage and how the bar and spiral patterns evolve. We do not know the precise masses and shapes of the dark matter halos, which set the depth of the potential and the strength of dynamical friction. Those uncertainties map into a range of scenarios from a very mild increase in encounter rates to something that is a factor of several higher than today's background for stretches of time. Observations in the first decades, like mapping local star densities and velocities with high precision, will narrow that down. In daily life, none of this shows up as a sudden change in the color of the sky or in the path of the moon. It shows up in the statistics of long-period comets a long time from now, in the slow drift of the Sun's galactic coordinates, and in the change in the distribution of stellar neighbors across centuries to millennia. For planetary defense, the takeaways are concrete. Keep watching the sky for comets and asteroids, because the long game says more of them may be on the way over million-year spans. Keep tracking nearby stars precisely, because the ones that will matter most will be those that invite themselves into the outer solar system in the far future, and recognize that the solar system's own architecture is resilient. It has survived passages through spiral arms, molecular clouds, and minor interactions before. A major merger lifts the background activity, but it does not rewrite the rules that keep planets bound to their star. So the fate of the solar system in this scenario is not a single dramatic swing, but a layered set of slow shifts. The orbit around the galaxy becomes a little more chaotic and a little puffier. The odds of distant stellar and cloud encounters rise, which eventually increases the supply of comets visiting the inner planets. Rarely stars get tossed into the halo or even out of the system altogether, and there is a tiny chance the Sun could be one of them. But the more likely outcome is that it stays bound, wandering farther from its birthplace than it might have otherwise. Through all of that, the planets remain in their lanes, the seasons continue, and the most noticeable practical difference for a long time is that careful watchers will have more comets to catalogue and more subtle motions to measure as the solar system rides out the long reshaping of its galactic home, while the planets keep circling calmly and the long game plays out in slow motion for us. The truly messy action is in the gas. Stars mostly slide past one another, but gas clouds do not. They hit, they compress, they heat, and they radiate. That difference is why, once the disks interpenetrate, the most dramatic physical changes unfold in the interstellar medium. You can picture several flavors of gas moving through each other at different angles. There is cold, dense molecular gas where stars can form. There is a cooler neutral component that is more diffuse. There is warm, slightly ionized gas that fills big cavities. And there is already some hot, very thin plasma in the halos. When the encounter begins, streams from these components meet head-on or shear past, and the first real consequences are shock fronts that thread through the contact zones. A shock in this context is just a sharp jump in pressure, density, and temperature that appears when gas is forced to slow down abruptly. The relative speeds between pieces of the two disks are high enough that these shocks are strong. In dense places, the compressed gas can cool quickly by radiating light, so the shock turns into a thin, bright ridge with a big pressure spike. In thinner places, cooling takes longer, so the gas stays hot and puffy and glows in X-rays. Both behaviors can happen in different layers, sometimes stacked on top of one another along the same line of sight. The important point is that the collisionless stars sail on, but the collisional gas piles up, and piled-up gas is the raw material for new stars. Along the leading edges where the disks slice through each other, you get long lanes of compressed gas. These lanes are not perfectly smooth. They wrinkle and fragment because turbulence and magnetic fields fight with gravity. Where the pressure is highest, Clouds collapse faster, and those are the spots where clusters of massive, short-lived stars begin forming. To an observer, these patches light up as glowing shells of ionized hydrogen around the newborn clusters. Those shells are lit by ultraviolet light from the hot stars, and they trace the outlines of the densest gas. The pattern is often beaded rather than continuous. Bright knot, faint gap, bright knot again, each knot mapping a pocket of high density squeezed out by the shock. Because the overall encounter torques the disks, gas also loses angular momentum and flows inward along dust lanes toward the inner regions. Bars, those elongated stellar patterns that grew stronger under the tidal push, are particularly good at setting up those lanes. Gas inside the bar's influence tends to crowd along its leading edges, then shocks and migrates inward. Near certain radii, the orbital resonances with the bar corral gas into rings. Those rings are star factories. You see them as sharply defined, bright circles or polygons around the galaxy center, full of young clusters and supernova remnants. The inner ring is fed by the inflow along bar lanes. So, as long as the bar stays strong, the ring can keep forming stars at a high rate. All of this extra compression lifts the star formation rate in the overlapping disks. Instead of a quiet pace, the system swings into a burst phase. Dust around the young clusters soaks up the ultraviolet light and re-emits it in infrared, so the total infrared output climbs steeply. This is why many merging systems are so bright in infrared images. They can cross the threshold that astronomers call the luminous infrared regime, where most of the energy is carried at long wavelengths. That does not mean the optical sky becomes blinding. For everyday human eyes, the changes are subtle. But if you look with infrared detectors, the map lights up, and if you measure how much power is coming out in total, you can tie it directly to how many new stars are being born each year. Starbursts bring feedback, which is the short way of saying that the newborn stars immediately start changing their environment. Massive stars blow strong winds. After a few million years, they explode as supernovae. Each supernova pumps energy and momentum into the surrounding gas, and the combined effect from thousands to millions of them stirs the whole region. You get cavities where the hot gas has cleared out, shells where the shock has swept material into a rim, and filaments where colder gas resists and gets stretched. In places where the surface density of gas is high enough, these effects layer on top of one another and set up large-scale outflows. Those outflows prefer to blow out of the plane, along the path of least resistance, which is why you see bipolar bubbles lifting above and below the disks in X-ray and radio maps of known starburst galaxies. The outflow speed depends on how much energy per unit mass is being injected and on how much mass is being carried along. Astronomers talk about the mass loading of a wind, which just means how much gas the wind is sweeping up compared to how much the stars are injecting from their own material. High mass loading makes a slower, denser wind that can carry lots of metals, which are the heavy elements cooked up in stars, into the galaxy's halo. Lower mass loading gives a faster, thinner wind that can punch farther out. In any case, these superwinds are not smooth cones. They are clumpy and time variable because the star formation that drives them is clumpy and time variable. Seen in X-rays, you spot ragged bubbles and chimneys. In radio, you trace electrons spiraling in magnetic fields as they are accelerated by shocks. In optical light, you see filaments of warm gas lifted by the pressure from the hot wind behind them. At the same time, the shock lanes in the overlap region do not sit still. Shear between different flow directions generates turbulence. That turbulence both supports gas against collapse in some places and enhances mixing that can feed future collapse in others. The end result is a patchwork where some clouds are shredded and others are gathered. Magnetic fields thread through all of this. They can channel gas along certain directions and make shocks more or less efficient at compressing material, depending on their geometry. The fields also help hold together the thin, long filaments you often see in deep images of interacting systems. One side effect of tidal forces is that they fling gas out into the tails along with stars. Those tails are not just pretty shapes, they are reservoirs. Gas in a tail can cool and fragment and form stars in situ, often in loosely bound groups that look like tiny galaxies. These are sometimes called tidal dwarfs. They are not dwarfs in the sense of a long, independent history. They are newborn clumps assembled from material stripped out of the disks. Their stars are relatively metal-rich compared to primordial dwarfs because the gas they formed from had already been through rounds of star formation before being flung into the tail. Many of these little clumps will fall back later, raining onto the remnant and adding to shells and loops around the future central body. In the central few hundred parsecs, where gas is funneled most strongly, conditions can become extreme. Densities rise. The rate of supernovae per unit volume goes up. Pressure grows. There are two intertwined consequences. One is purely stellar. A compact, intense nuclear starburst that builds a dense central population in a relatively short time compared to the age of a galaxy. The other involves the central black hole, which can start swallowing some of this inflowing gas and turn into an active nucleus with a bright accretion disk and possibly jets. Those central pieces deserve their own deep dive because the radiation physics is different from the general starburst. But the trigger is the same inflow that bars and shocks set up. Gas physics has its own timelines. Small clouds can collapse into stars in a few million years once they are pushed over the edge by a shock. Big complexes take longer, but they also produce more clusters. The first supernovae from the most massive new stars can explode after only a few million years, so the feedback cycle starts quickly. The rising supernova rate then keeps stirring as the next rung down in mass ends their lives tens of millions of years later. The whole starburst episode can last tens to hundreds of millions of years in one region, and additional passages in the galactic dance can light up new zones and prolong the activity. Over that span, a large fraction of the available cold gas can be consumed or heated to the point where it is no longer efficient at making stars. As gas is used up and blown out, the starburst throttles itself. The infrared brightness fades. The outflows slow and break into fountains that may fall back later. The system heads toward a phase where the remaining gas is hotter and more diffuse, sitting in a big halo and cooling slowly. That is one reason a major merger often leads to a more spheroidal remnant with a lower ongoing star formation rate. The dramatic blue knots and red emission regions retreat, and the light becomes dominated by longer-lived, redder stars. The efficiency of this shutdown depends on how much gas the galaxies started with, how strongly the bars and shocks concentrated it, and how powerful the feedback was. In gas-rich encounters, you can get multiple bursts as inflows resume after each flyby. In gas-poor encounters, the activity is modest and fades sooner. From the ground, you would not feel any of this, but telescopes would. Radio dishes map the cold gas by looking at emission from molecules like carbon monoxide, which act as tracers for the otherwise invisible hydrogen. Those maps would show gas piling up in ridges, draining along bar lanes and being drawn out into tails. The profiles of the emission lines would broaden where shocks add turbulence. In the infrared, space telescopes would track warm dust and complex molecules excited by ultraviolet light from young stars. The glow would trace out the overlap region and highlight the rings near the centers. Optical spectrographs would separate the signature of shock-excited gas from gas lit by starlight because shocks produce different line ratios, a simple diagnostic that lets you draw boundaries on a map between shock fronts and star-forming zones. X-ray observatories would watch the hot phase as bubbles inflate and leak. None of these instruments would show an overnight flip, but in months and years they would record growth and motion that goes well beyond the slow drift of the stars. There is also a quiet chemical story playing out. Every round of star formation and feedback enriches the gas with heavier elements. The outflows carry some of those elements into the extended halo and even into the space between galaxies. Later, some of that enriched gas can cool and rain back in, seeding the next generation of clouds, or it can escape to join the more general circumgalactic medium. Over long times, this is how galaxies build the metal content we measure in their stars and gas today. In a merger, the rates are simply sped up and concentrated. You push more gas through the cycle in a shorter time, so you leave a stronger imprint on the chemical gradients. Another piece to keep in mind is the role of shear and rotation. It is not enough to just compress gas. You have to do it in a way that overcomes the tendency of rotation to tear structures apart. In the dense ridges and rings, the balance tips in favor of collapse because shock compression raises the density and higher density fights back against shear. In the lower density overlap zones, the gas may be stirred more than it is compressed, and there the net effect can be to raise the pressure without making many stars. That is why star formation in mergers is patchy. You get fireworks near the bar ends, in nuclear rings, and in clumps along the overlap lane, while large stretches in between remain uneventful, despite being bright in diffuse emission from heated gas. As for what the Earth receives from all this activity, the strongest signals come as light and particles over long periods. The local risk from one specific supernova remains tied to distance. Nothing about the starburst makes a faraway event suddenly dangerous. What it does is raise the background number of such events in the system, especially near the centers and along the densest ridges. For us, the practical effect is an increased flow of data, not a change in daily conditions. Observatories will catch more supernovae lighting up distant patches. Radio arrays will register more non-thermal emission from electrons accelerated in shocks. Spacecraft will report subtle increases in the diffuse backgrounds that need to be subtracted from other observations. Those are jobs for instrumentation and data analysis, not reasons for alarm. Tucked within the grand drama are many small laboratories for physics. Shock fronts let us test how magnetic fields guide charged particles and how quickly those particles gain energy. Filaments and clumps reveal how turbulence cascades from large scales down to small ones. Ring structures near the centers measure the positions of resonances set by the bar, which in turn tell us about the distribution of mass and the pattern speed. Tidal dwarfs show us how star formation proceeds in gas that is almost free of dark matter. Each of these little niches becomes accessible in a way it is not when the nearest textbook example is far across the universe. This time the arena is spread across our own sky, big enough to map in detail and slow enough to watch evolve across years and decades. Eventually, as the inflows ease and the gas reservoir thins, the tumult settles, the shock lanes weaken, the nuclear ring empties or breaks apart. The outflows lose their driving and collapse back. Much of the remaining gas is left hot and dilute, reluctant to cool, and the bright star-forming knots fade. What remains is a smoother, more pressure-supported system where random motions dominate over the tidy rotation that once organized the spiral arms. That transition is not a single moment. It is a gradual shift as each pocket runs out of fuel and as the feedback from previous bursts keeps the surroundings too warm to condense quickly. In that way, the gas physics not only lights up the merger, but also helps steer it toward a quieter end state, shaping the path from two structured disks to one rounder, redder remnant. As that gas-driven remodeling pushes material inward and turns large, ordered spirals into thicker, rounder structures, the next obvious question is what all that inflow does at the very centers. The same gravitational torques and shock lanes that concentrate gas into rings and ridges also feed the nuclei, and in both galaxies the nucleus hosts a supermassive black hole. The one in our Milky Way, Sagittarius A star, weighs about 4 million suns. The one in Andromeda is far larger, well over 100 million suns. Those numbers matter because they set the scale for how bright and how energetic the central regions can become once fuel is available. In the first days and weeks, the story is modest. Gas needs to lose a lot of angular momentum to make it from kiloparsec scales, which is thousands of light-years, down to parsec scales, which is a handful of light-years, and eventually to the sub-parsec zone right around the black hole where the accretion disk forms. Bars and spiral shocks get you part way. Inside the innermost ring, turbulence, magnetic stresses, and smaller-scale gravitational instabilities take over. This is not an overnight delivery. Still, small changes appear early. You would see slightly harder X-ray spectra from both centers, a sign of hotter, denser surroundings, and short radio flares as pockets of gas fall inward and get heated. As the months give way to years and decades, the inflow strengthens. The inner rings brighten in infrared as dust warms, and more gas crosses the final hurdles to reach the nucleus. When gas spirals in to within a few light days of the black hole, it forms a hot, bright accretion disk. That disk shines across the spectrum. If the supply is steady enough, the black hole can enter an active phase, the familiar active galactic nucleus state. There is a ceiling to how bright it can become for a given mass, set by the balance between the inward pull of gravity and the outward push of the radiation it produces. A limit astronomers call the Eddington limit. A black hole with over 100 million solar masses can, in principle, radiate as brightly as the combined light of trillions of suns without blowing away all its fuel. But in practice, most active phases sit below that ceiling and vary a lot. Dual activity is very possible here. Both centers have access to extra fuel at the same time, and observations of other mergers show that it is not rare to find two bright cores separated by a few tens of thousands of light-years. From Earth, that would look like a pair of compact sources glowing in X-rays and mid-infrared, each with spectra that carry the fingerprints of fast-moving gas near a black hole. Those fingerprints include broad emission lines from gas whipping around at thousands of kilometers per second and narrower lines from clouds farther out that are lit by the nucleus. Because dust can block the optical light from these cores, the clearest view might come in hard X-rays and in radio wavelengths, where obscuration is less of an issue. If the inflow is strong and the central engine spins up, jets become likely. A jet is a narrow, fast stream of particles and magnetic fields launched from the region very close to the black hole, probably powered by the rotation of the hole and the tangled fields in the inner disk. Jets run best when the black hole is spinning fast and the inflow is well organized. They can pierce out into the surrounding gas and blow cavities. In radio maps, you see these as lobes, bubble-like zones filled with relativistic particles. In X-rays, you see rims where the shocked gas is compressed and heated by the expanding cavities. In optical images, you may catch narrow filaments of excited gas tracing where the jet interacts with denser clumps. From a habitability standpoint, what matters is orientation and distance. The Milky Way's center is roughly 26,000 light-years away. Andromeda's center, in our contrived near passage, is also tens of thousands of light-years from us. Even a powerful nucleus at those distances delivers a diffuse bath of high-energy photons compared to the Sun and the local stellar neighborhood. A jet would need to be pointed very close to our line of sight for a long time to create serious irradiation, and the odds of that alignment are low. The more plausible outcome is a small rise in the background of high-energy photons and cosmic rays over long stretches, and those are things Earth's magnetic field and atmosphere already screen fairly well. The real caution zone lies within a few tens of light-years of an active source, and we are orders of magnitude farther away than that. As the two galaxies swing past their first close approach and begin the slow dance toward coalescence, the central black holes respond to the global dynamics too. Each sits in the core of its stellar bulge. Those bulges and the surrounding dark matter feel dynamical friction as they move through the combined sea of stars. Friction, in this sense, is gravity creating a trailing overdensity, a wake that tugs backward on the moving mass. It robs orbital energy and angular momentum, so after each pass, the separation shrinks. Eventually, the two cores come close enough that the black holes are embedded in a shared nucleus. From there, the pair sinks inward together and forms a bound binary. Once there is a binary, new channels open. The pair orbits inside a crowded nuclear environment filled with stars and gas. Stars that wander too close to the pair can be slingshotted out, stealing a bit of the binary's orbital energy and making the pair tighten. This three-body scattering is efficient while there is a steady supply of stars on intersecting orbits. As the binary hardens, it carves out a relatively empty region in the center by ejecting many of those stars, leaving behind a flatter central brightness profile called a core. Observers have seen these scoured cores in massive elliptical galaxies and interpret them as the footprint of past black hole binaries. There is also gas to consider. If a circumbinary disk forms around the pair, meaning a disk of gas that orbits both black holes, its torques can drive the two closer still. Inflowing streams can feed little mini-disks around each black hole and make the system flicker in distinctive patterns. Those patterns would show up as periodic or quasi-periodic changes in brightness across many wavelengths, with cycles tied to the orbital period of the binary, which could be anywhere from months to thousands of years depending on separation. For human observers, cycles lasting years to decades would be the ones we can track directly. At small separations, a different form of radiation takes over as the main drain on the binary's energy: gravitational waves. These are ripples in spacetime that carry energy away as the pair orbits. The frequencies for such massive binaries are low, with cycles lasting minutes to hours rather than fractions of a second. That puts them squarely in the range of planned space-based detectors that use long baselines to sense tiny distance changes between spacecraft. A mission like that could watch the final years of the inspiral of a pair like Andromeda's and the Milky Way's, tracking the slow rise in frequency and amplitude as the black holes spiral together. On Earth, you would not feel these waves. They pass through everything and change distances by a fraction far smaller than an atom across a kilometer. Only exquisitely sensitive instruments can measure them. When the black holes finally merge, they emit a sharp burst of gravitational waves and settle into a single, more massive black hole that rings down, losing the last deformations in a damped oscillation. There is also a recoil. Because the waves carry momentum and because the emission is not perfectly symmetric, the remnant black hole gets a kick. Depending on the mass ratio and the spins, that kick can range from a few tens to a few thousand kilometers per second. In our case, with a mass ratio between roughly 1 to 1 and 1 to several, kick speeds of a few hundred kilometers per second are plausible. The central gravitational well of the merged galaxy is deep, so the remnant would almost certainly remain bound. It would oscillate around the center for a long time before settling, and during that time, it could light up as an offset active nucleus if gas is available. All the while, stars keep feeding the nuclei in rarer, more dramatic ways. Occasionally, a single star wanders too close and gets torn apart by tidal forces. That produces a tidal disruption event, a flare that brightens over weeks and then fades over months to years as the debris rains down. The rate of these events can rise during and after a merger because the change in the central potential shakes stars onto risky orbits. These flares give a direct way to weigh the black holes and to study the physics of extreme gravity using light curves and spectra. For life on Earth, they are harmless flashes from far away, but for astronomers, they are clean probes of the central engine. Another byproduct of the binary phase is a population of hypervelocity stars. When a star interacts with a tight binary, it can get flung out at very high speeds, enough to escape the galaxy altogether. Surveys of the Milky Way already hint at such stars today. In a merger, the rate could increase as the binary hardens. If we end up with a good vantage point, we could see a spray of fast-moving stars radiating from the center over millions of years, each one a breadcrumb marking past interactions with the pair. It is useful to be realistic about the light show from the centers. An active phase can reach enormous luminosities, but dust and gas near the plane can hide a lot of the optical and ultraviolet output from our line of sight. Much of the energy gets absorbed by dust and re-emitted in the infrared, which is bright to telescopes but not to human eyes. X-rays and gamma rays come through more directly, and they would make the sky busier in those bands. Space missions designed to monitor high-energy radiation would see the centers flicker and flare more often and more strongly than they do today, and those data would tie directly to the gas dynamics we are already watching in the overlap regions. The timeline for all of this stretches. Bars and shocks start funneling gas inward within thousands to millions of years. The first real active phases could turn on within tens of millions of years as the inner reservoirs fill. The formation of a hard black hole binary takes longer, hundreds of millions of years after the first close passage, and the final coalescence often lands around 1 billion years after the interaction begins, depending on the initial orbit and the total masses. Those are big numbers, but the early steps are still observable. Periodic signals from a wide binary, fresh outflows from a rejuvenated nucleus, and rising rates of tidal disruption flares can show up much earlier, and each one tells us where the system sits on that path. Risks to habitability from the central action remain the same kind of story you heard for the broader starburst: distance and alignment rule. The Earth is not near either nucleus. Even a bright, long-lived active phase creates a modest hike in high-energy photons at our location compared to the day-to-day flux from the Sun and to the occasional nearby supernova in our own neighborhood. The worst case would be a jet aimed almost directly at us for an extended time, and that requires a geometry that is unlikely. On top of that, the jet itself may be intermittent, changing direction slightly as the inner disk precesses and being slowed by encounters with cold gas near the center. So the prudent stance is to pay attention and to harden technology that is sensitive to high-energy radiation, not to fear apocalyptic beams sweeping across the planet. For observers, the centers become a multi-messenger playground. Light across all bands shows how gas is moving, heating, and cooling. Neutrinos could arrive from the most energetic regions where protons are accelerated and collide, although detecting them from such distances is hard. Gravitational waves give a pure probe of the final smash-up, giving masses and spins with high precision. With all those channels together, we can test the connections between galactic-scale torques that move gas inward and the sharp, fast physics right outside a black hole's event horizon. We can also check the long-suspected link between black hole growth and the growth of the bulge, because a major merger offers both ingredients at the same time, a supply of fuel and a mechanism to deliver it. When the dust settles, literally and figuratively, the central black hole in the remnant will be significantly larger than either progenitors. The previously carved core in the stars will be broader. The pace of central activity will drop as the easy fuel is spent and heated gas lingers in a hot halo. In the end, the nucleus becomes a mostly quiet, massive object at the heart of a rounder galaxy, with sporadic flares when the occasional cloud wanders in or a star's orbit decays too far. The path to that endpoint is what makes this scenario scientifically golden. It ties the inflow you can map across the sky today to the fireworks in the centers and at the very end to a clean gravitational wave event that tells you exactly what mass and spin the final black hole carries. All of that unfolds even while life in the outskirts continues under familiar conditions, because at our distance, the central fury is a show for instruments and a background glow for the rest of us. Since the central fireworks mostly register as a show for instruments at our distance, the practical question turns to radiation and what, if anything, that means for life and technology. The short version is that a merger can raise the background of high-energy particles and ultraviolet light over long stretches, and it can boost the frequency of rare bursts, but distance and shielding still set the actual risk for us. The Earth comes with a thick atmosphere and a magnetic cocoon, and those two defenses handle most of what a busier galaxy can throw at them. Start with what we are even talking about. High-energy hazards arrive in two broad forms: photons and particles. Photons are packets of light, ranging from ultraviolet up through X-rays and gamma rays. Particles are mostly protons and heavier nuclei zipping around at near light speed. We call those particles cosmic rays. Photons go straight unless something absorbs them. Charged particles are different. Magnetic fields bend them, scatter them, and delay them. That difference is why you see a flash from a distant event at the speed of light. But the cosmic rays from the same event arrive dribbled out over long times because they wander through tangled fields. On human timescales, the first day and the first year after our contrived close pass, the radiation environment at the Earth barely changes. There is no invisible wall of gamma rays suddenly slamming into us just because Andromeda's disk appears nearby. The background of starlight and diffuse ultraviolet shifts subtly on the sky, but sunlight still dominates the surface by an absurd margin. The uptick that matters builds slowly as supernovae, shocks, and possibly an active nucleus accelerate more particles and shine more high-energy light over thousands to millions of years. That long buildup is the domain of monitoring and modeling, not of emergency alerts. Cosmic rays are produced efficiently in supernova remnants and in large-scale shocks that form when gas flows collide or blow out of starburst regions. A merger increases both of those. The star formation rate rises, so more massive stars live fast and die as supernovae, and the shocked overlap region and the outflowing winds give long stretches of accelerating structures. Still, the way cosmic rays reach us matters. They do not beam in like light. They diffuse through the magnetic fields in the galaxy. Think of it as a random walk across the tangled field lines of the disk and the halo. That random walk stretches their travel time from a straight shot to a long meandering journey. The upshot is that even if the source power jumps, the flux at any one place climbs gradually and varies gently with time. What would that feel like at the surface? At sea level, the dose you get from cosmic rays today is a small fraction of your total natural background. Most of the dose from the sky comes from muons, which are secondary particles made when cosmic rays hit the upper atmosphere and start cascades. Those muons are penetrating and reach the ground easily. If the galactic cosmic ray flux doubles over long times, the ground-level dose from muons might rise by roughly a similar factor, but keep perspective. We are talking about an addition at the level of a few millisieverts per year or less, not a catastrophic jump. It is more noticeable at high altitudes because the atmosphere is thinner there. Airline crews already receive higher doses on long polar flights than people at sea level. In a slightly hotter cosmic ray climate, operators would tweak flight profiles occasionally during solar quiet periods to manage exposure, just as they already do during strong solar particle events. The poles matter because the Earth's magnetic field funnels charged particles toward high latitudes. The field lines open near the poles, so the atmosphere there takes more of the incoming. That is why polar regions see more auroras and why radiation doses on polar flight routes are a bit higher. In a merger-driven starburst phase, the baseline of galactic cosmic rays could climb modestly, and you would see that first at high latitudes. You might also notice more frequent ground-level enhancements, which are brief spikes in secondary particles detected by neutron monitors and muon counters. But those are mostly tied to solar eruptions, not to distant galaxies. A busier galaxy sets a higher baseline. The sun still controls the day-to-day fireworks through its own storms and cycles. There is a bigger lever than a raised baseline, and that is a nearby supernova. The range that matters for biology on the surface is on the order of a few tens of light years. Inside that bubble, you can get ozone depletion and an increase in ultraviolet reaching the ground large enough to stress ecosystems for years. Outside that bubble, the effects taper quickly. During a merger, the overall supernova rate rises, but it rises mostly where the stars are forming, which is along dense ridges and near the centers. We are tens of thousands of light years from those zones. What changes for us is the long-shot probability that a supernova goes off close by because the local density and the mix of stellar ages around us shift as the disk thickens and warps. That probability climbs, but from a very low baseline. In a quiescent Milky Way disk, a supernova within a few tens of light years is a once in many hundreds of millions of years event. Doubling or tripling a very small number still leaves it very small on human and even on civilizational timescales. It is not zero, and it is worth tracking because the consequences are real if it happens, but it is not a reason to expect near-term biological stress. If such a nearby event did occur, the mechanism for surface impact is mainly chemistry in the stratosphere. High-energy photons and cosmic rays ionize molecules and make reactive nitrogen and hydrogen compounds. Chemists call them odd nitrogen and odd hydrogen because they do not pair up in the usual way. Those compounds catalyze the destruction of ozone. Less ozone means more ultraviolet B getting to the surface. Ultraviolet B is the band that can damage DNA and proteins and suppress photosynthesis. The depletion would not be uniform. It tends to be strongest at high latitudes and to vary with seasons because stratospheric dynamics matter. Ice core records on Earth show spikes in nitrates that point to past solar particle events, which are much smaller than a nearby supernova, but they give a sense of the chemistry at work. In the supernova case, models suggest ozone losses that could reach tens of % for years if the event is close enough. Farther away, the effect shrinks quickly. During a merger, the risk envelope is the same. The only change is that the draw from the cosmic lottery happens slightly more often over very long periods. Gamma-ray bursts are a different beast. They are narrow jets from catastrophic events like the collapse of a massive star's core or the merger of neutron stars. They are far rarer than supernovae and much more directional. If one hits you, the pulse is intense, but only if the jet points almost exactly at you, and the safe distance is thousands of light years. In a starburst phase, the rate of the long kind, which come from massive stars, could go up in dense, star-forming regions. We are not in one of those regions, and the geometry has to be terrible for us to take a direct hit. That combination of rarity, distance, and the requirement for precise aiming keeps gamma-ray bursts low on the list of credible threats for our location. An active galactic nucleus is steadier and more spread out than a burst. If either the Milky Way's center or Andromeda's center lights up for a while, the added flux of X-rays and gamma rays at our distance will be modest compared to the Sun's day-to-day output in the biologically relevant bands. Space weather for Earth is set mostly by our own star. Solar ultraviolet and solar energetic particles drive ionization in the upper atmosphere, heat the thermosphere, and fuel auroras. Geomagnetic storms that can disturb power grids and satellites come from coronal mass ejections, not from faraway galaxies. A livelier cosmic background nudges those systems at the edges, but it does not take control of them. There is a long-standing idea that cosmic rays could influence clouds by making more of the tiny aerosols that water condenses on. The data on that are mixed. In lab chambers, ionization can help form some kinds of particles under the right chemical conditions. In the real atmosphere, the effect has to compete with a zoo of other processes that make aerosols and set cloud lifetimes. Correlations in the past between cosmic ray proxies and climate are not consistent enough to claim a strong, simple connection. In a merger era, it is fair to expect more ionization in the lower stratosphere and upper troposphere, especially near the poles, and to look carefully for subtle shifts in cloud microphysics and in lightning rates. It is not fair to promise dramatic cloud changes that rewrite climate. Climate remains dominated by solar output, greenhouse gases, aerosols from volcanoes and industry, ocean heat content, and internal variability. Cosmic rays are a tweak, possibly measurable with enough data and careful attribution, not a master switch. Technology is a cleaner story because electronics respond directly to high-energy particles. Cosmic rays can flip bits in memory, punch through detectors, and cause single-event upsets that crash systems. Satellite builders already harden components, add error correction, and design redundancy to ride through these blips. A higher background means you get a few more blips per unit time. That is handled by more robust error correction and by shielding in sensitive packages. For spacecraft outside the Earth's magnetosphere, like lunar or Martian missions, the background matters more because there is no planetary magnetic field and less atmospheric shielding. In a hotter cosmic ray climate, mission planners would add a little extra mass to storm shelters, park water or fuel tanks around crew quarters, and tweak trajectories to minimize time in the highest flux regions. These are straightforward engineering responses. Aviation already lives with this. On polar routes, flight planners sometimes change altitude or timing during solar particle storms to keep crew doses within recommended limits. A merger era does not add new kinds of events, it slightly raises the baseline. That means more conservative thresholds might be used more often in quiet solar conditions, especially for frequent flyers and cabin crews. On the ground, the main infrastructure worry is not cosmic rays, but geomagnetically induced currents during solar storms. Those depend on the solar wind and on the coupling of the interplanetary magnetic field to Earth's field. A busier galaxy does not make those storms more likely. Keeping power grids safe remains a space weather job focused on the Sun, not on the distant centers of galaxies. For biology beyond Earth, the merger matters in a location-dependent way. Planets near the central kiloparsec, which means the inner few thousand light years, will see higher backgrounds of ultraviolet and cosmic rays if a sustained active phase or a strong starburst is underway. Clouds of gas and dust can shield to some degree, but within that inner zone, the rate of nearby supernova goes up, and the odds of a gamma-ray burst being closer rise. Habitability there is tougher during the active period. Far out in tidal tails and in the outer halo, the environment gets quieter with fewer nearby massive stars and lower event rates. If the Sun eventually wanders outward, as discussed before, the long-term radiation environment for us could actually soften compared to the inner disk. It is worth touching on timescales to keep expectations grounded. The first hours and days bring no meaningful change to radiation at the Earth's surface. The first years and decades bring an amazing show in telescopes and perhaps a barely measurable uptick in diffuse high-energy backgrounds in space. The first thousands to millions of years bring a stronger shift as the starburst ramps, supernovae multiply, and outflows fill with energetic particles. The earliest clear biological signals would come not from the slow background climb, but from individual nearby events, and those remain unpredictable and rare. That is why the practical approach leans so hard on monitoring. Neutrino detectors to give hours of warning for a very nearby supernova, all sky-high energy telescopes to watch for bursts and active centers flaring, ground networks of neutron monitors and muon telescopes to track the particle rain, and atmospheric sensors to follow ozone, odd nitrogen, and odd hydrogen chemistry. There is an honest uncertainty budget. We do not know exactly how much the cosmic ray flux would increase at our position, because that depends on the details of the gas flows, the star formation history, the strength and structure of the magnetic fields, and how quickly the accelerated particles escape. We do not know the exact path the Sun will take through the stirred-up disk, and local density matters for nearby supernova odds. Even the Earth's magnetic field is not constant on long times. It wanders and sometimes reverses, and field strength influences how much low-energy cosmic rays reach the atmosphere. All of these knobs introduce a spread in outcomes. That is not a reason to hand-wave. It is a reason to set up measurements now and continue them steadily, because long baselines turn uncertainty into clarity. As for daily life under a grand merger sky, the sensible posture is curiosity with a pinch of precaution. Invest in radiation hardening for satellites and deep space missions. Keep air traffic protocols nimble for rare spikes. Maintain and expand atmospheric chemistry monitoring so that if a nearby supernova does happen, we can watch how the stratosphere responds in real time. Teach the difference between solar storms and galactic backgrounds so that power grid operators and the public are not spooked by the wrong thing. And keep expectations straight. The show in the heavens is spectacular, the science is rich, and the hazards at our location are modest and drawn out over long spans, spiking only if a rare event happens uncomfortably close. In the end, the merger nudges the radiation climate rather than flipping it. The Earth's defenses are strong, and the distances involved are huge. A livelier galaxy brings more supernovae in faraway neighborhoods, more diffuse particle winds in the halo, and occasional flickers from central engines that have finally found fuel. The things that would matter most for habitability here are still the rare local ones, a supernova in our backyard or a solar tantrum in our own star. Everything else is a background that instruments will map and models will fold into forecasts, while life under our atmosphere carries on much as it does now, with one eye on the sky and a steady stream of data telling us how the high-energy weather is evolving. With that radiation story set as mostly a slow nudge rather than a sudden threat, the next natural question is how fast anything else actually changes that we could notice, because timing shapes what matters for people, for instruments, and for the solar system. The simple way to lay it out is to start in hours and step outward to eons, keeping an eye on what shifts from one phase to the next. In the first hours and days, the change is almost entirely what you can see and record with cameras and spectrographs. The new panorama across the night sky is instant because we set the initial condition that way, and instruments start pulling down spectra and velocity maps right away. Gas in the overlap zones begins to heat where counterflowing streams meet, and you can already pick up those first hints in radio and X-ray data. Mechanically, nothing important happens to the solar system in that window. Earth's tides, the moon's path, the constellations, all of that stays steady. This moment is about setting baselines because later comparisons depend on knowing exactly how things looked at the start. Weeks to months in, you still do not feel gravity do anything dramatic locally, but the data become richer. Velocity fields of gas are mapped with high resolution, showing where flows shear and where the first shocks are shaping up. Warps in the Milky Way's outer disk that existed already can be measured more cleanly against the background of the newcomer's disk, and small additional bends start to register in precise surveys of star positions. Newborn star clusters from gas compression do not pop up yet. The clock for forming stars is measured in millions of years, not months. A few supernovae will light up here and there because massive stars from ongoing star formation in both galaxies are reaching the ends of their lives. But the overall rate this early is not a merger story. It is just the sharp view of what was already in progress. Across years to a couple of decades, measurements of star motions become the real product. Astrometry, which is precise mapping of positions and their drift, builds an archive of how stars slide across the sky. You will not track a star's path with your eyes, but space missions and long baseline interferometers can register tiny changes that reveal coherent streaming motions set up by the combined gravitational field. In the gas, the overlap shock lanes get better defined. Radio maps show neutral hydrogen piling into ridges. Infrared images track dust warming along those lanes. Astronomers release the first full sky mosaics that show faint tidal bridges beginning to grow, the kind that you would not notice by eye but that are obvious in stacked exposures. The solar system keeps orbiting the same way it has while the stage for long-term rearrangement gets clearer. Over a few centuries, the pattern of slow change is now measurable in multiple ways. The Milky Way's thin disk starts to thicken imperceptibly to ordinary stargazers, but measurably to surveys that count stars above and below the plane. The Sun's motion, relative to nearby stars, shows a small increase in random velocities as dynamical heating gently builds. You get the first definitive maps of long tidal streams stretching from the edges of both disks, which tells you the direction of angular momentum transfer and confirms the predicted torques. The overall light in the night sky looks much the same, aside from the moving traceries of nebulae and star-forming patches captured by telescopes. This is the era when scientists lock down the early trajectory and refine models against reality. Scale up to a few thousands to tens of thousands of years, and two threads start to matter more. One is the slow inflow of gas along bar lanes toward the inner rings, which brightens those central regions in infrared, and then, once massive stars appear, in ultraviolet and H-alpha light that traces ionized hydrogen. The other is the very earliest stirring of the Oort cloud by the baseline increase in stellar encounters in a thickened, slightly denser neighborhood. These are statistical shifts. You will get a higher rate of very distant flybys that subtly rearrange comet orbits at the fringes. Those comets take hundreds of thousands to millions of years to fall inward, so there is no immediate shower, but the seeding of future waves begins. By hundreds of thousands of years, the first extra trickle of long-period comets from the Oort cloud that were nudged early in the encounter can start to arrive at the inner solar system. Planetary defense teams will see a modest increase in new, long-period comet discoveries compared to 20th century and early 21st century baselines. Most will be deflected by Jupiter and Saturn or ejected after a pass or two, as happens today, but the statistics of potential impactors will skew upward somewhat. In space, the cosmic ray background begins to climb gently as the first rounds of merger-driven supernovae and large-scale shocks feed particle acceleration. At the surface, any dose change is small, more noticeable at high altitude and high latitude than elsewhere. Over a few million years, the starburst pattern becomes obvious. The overlap region lights up with chains of young clusters. The bar-fed inner rings around both centers turn into major star-forming zones. Supernova rates rise along those lanes, and X-ray bubbles from hot outflows grow above and below the disks. The shock fronts that instruments hinted at early on are now fully formed, and their boundaries are mapped across all wavelengths. The Milky Way's spiral structure looks washed out compared to today because random motions in the disk have increased and warps have grown, and Andromeda's structure shows similar thickening and deformation. Dual-active nuclei are a real possibility in this window if gas inflow continues and dust does not block our line of sight too badly. You would not see those with unaided eyes. Telescopes would do the heavy lifting, just as they do now, for distant active galaxies. Tens of millions of years into it, you expect the first big pulses of feedback to peak and the first serious superwinds to push out. The circumgalactic medium, the huge halo of thin gas around the galaxies, fills with enriched material carried by these winds. Some of it rains back later in fountains, some of it escapes farther out if the winds stay fast. The disks are thicker, the bars stronger, and the resonant rings around the centers have cycled through bursts of star formation and partial depletion. Tidal tails are long and populated with clusters and, in some cases, with small tidal dwarf systems that formed from stripped gas. If you were an amateur astrophotographer under a very dark sky with a large instrument, the faint outer arcs and shells would be the new targets that reward very long integrations and careful processing. At a few hundreds of millions of years, the overall orbital dance brings the galaxies through another close passage, unless the initial setup was so closely tuned that they sank inward without rebounding. With each pass, dynamical friction removes more orbital energy, so the separation shrinks and the approach becomes more direct. The thin disks we started with are now largely transformed into thicker, puffier stellar distributions with strong bars and remnants of spiral patterns embedded in them. The central regions have grown denser. The total star formation rate begins to plateau or even decline as gas gets consumed and heated, although inflows during a fresh pass can briefly revive activity in specific zones. Human timescales are tiny compared to this, so this is about what a series of distant descendants would document, not what a single society would watch year by year. Around 1 billion to 2 billion years after the start, the two central black holes are likely to have formed a gravitationally bound pair and then tightened to the point where gravitational waves take over as the main energy sink. The final coalescence could come in that window, producing a burst of low-frequency gravitational waves that space-based detectors can track, and a recoil that might offset the new central black hole slightly from the stellar center for a long time. The galactic light profile by then is already well on its way to looking like a single, rounder system rather than two overlapping spirals. The starburst has throttled back because the cold gas reservoir is much smaller, with a lot of the remaining gas heated and spread into a hot halo that cools slowly. Several billions of years down the line, the system relaxes into a spheroidal remnant. Stellar orbits are mostly random rather than organized in a thin plane. The central black hole is larger than either original one. The inner stellar distribution has a broad core from stars ejected during the black hole binary phase, and the outer body shows faint shells and loops from past tidal features that fell back. Star formation does not vanish entirely, but it is slow and patchy, tied to gas that cools locally or to minor accretions of dwarf galaxies that wander in. For an observer on a future world, the night sky is calmer in terms of bright blue star-forming patches and busier in terms of smooth red light and scattered globular clusters. While that long arc plays out, the Sun has its own clock. On timescales of hundreds of millions of years, the Sun gradually brightens as part of its normal evolution. On timescales around 4 to 5 billion years, it leaves the main sequence and expands into a red giant. Those milestones are independent of the merger itself. The encounter may change the Sun's galactic orbit, possibly moving it outward into the halo of the remnant or keeping it in a thickened disk. But the star's internal evolution proceeds on its own schedule. That means that by the time the remnant is fully settled, the Sun is already well into late life or has completed it, and any worlds still around are dealing with local stellar physics far more than with galactic environment. This timeline also sets expectations for practical science. In the first decade, you get improved maps and the first measurements that show departures from isolated disk dynamics. In the first century, you assemble long baselines that make warps and streaming motions unambiguous. In the first 1,000 to 10,000 years, you watch the overlap shocks mature and inner rings ramp up star formation. In the first 1,000,000 to 10 million years, you see the starburst in full and outflows carving cavities. In the first 100 million years and onward, you track the transformation from disk-dominated to pressure-supported structures and clock the approach to coalescence. At each stage, instruments and methods change. Early on, optical and radio surveys lead. Later, infrared and X-ray monitoring of central activity comes to the fore. Much later, gravitational wave observatories carry the key signal of the black hole merger. For everyday life, the timeline is reassuringly slow. Nothing on the scale of days, months, or even centuries forces changes in how we live under the sky beyond taking advantage of a spectacular view and dealing with a slightly busier high-energy background for technology. The first tangible geophysical marker from the merger is likely to be an uptick in long-period comet arrivals over hundreds of thousands to millions of years, which is a signal that would show up in catalogs and in cratering statistics rather than in anyone's lifetime experience. The strongest astrophysical drama, central active phases, giant outflows, and the final coalescence of black holes makes for amazing datasets and a deeper understanding of how galaxies grow. But from our vantage point, it is remote and slow. There is uncertainty in the exact timing because it depends on the masses, the orbits, and the gas content. If the halos are heavier than we think, dynamical friction is stronger and the coalescence is faster. If the encounter has more angular momentum, meaning more sideways motion, the pair will swing wider and take longer to sync. If the gas fraction is high, starbursts are stronger earlier and feedback can heat and blow out enough gas to alter later inflows. Observations in the first century or two will narrow these options quickly because the shapes of tidal features, the measured streaming motions, and the brightness of early star-forming rings tie directly to those parameters. The purpose of laying out timescales is not to fix exact dates, but to give the right sense of pace so that we know which changes to chase now and which to leave to the deep future. The headline is simple. Hours and days reshape the sky's look without touching the mechanics of our neighborhood. Years to decades give us precise maps of motion and the first clear signs of gas being squeezed. Centuries bake in those trends. Thousands to millions of years turn on the starburst factories and inflate outflows. Millions to tens of millions of years lean into morphological transformation as tails, bridges, and thickened disks dominate. Hundreds of millions of years bring repeated close passes and a slide toward a single body. A billion or two brings the merger of the central black holes and a steady decline in star formation. Several billions see the remnant as a rounded, calmer galaxy, while the Sun follows its own lifespan toward its red giant phase. Knowing that pacing lets us set our expectations fairly, enjoy the views we get, and design measurements that match the tempo of a universe that rarely hurries, even when two giant galaxies are finally sharing the same sky. Knowing that the pace is slow for us and fast only for telescopes, the logical move is to ask how people and institutions pivot to make the most of the moment and to manage the few practical risks. The first and most obvious reaction is observational. Professional observatories would flip their schedules almost immediately, not because danger demands it, but because the sky has turned into a live laboratory. Night after night, wide fields would be imaged to build a continuous record, and instruments that split light into its colors would measure motions and physical conditions across the overlapping disks. That sounds routine, but the scale is unusual. This is not a single target that you point at. It is the whole sky changing gently and unevenly. That forces a different style of observing, more like weather monitoring than one-off snapshots. Space missions would do the same. Ultraviolet and X-ray telescopes in orbit would set up rolling surveys of the contact zones where shocks are forming, and gamma-ray instruments would keep watch for brief flares and bursts. Infrared satellites would map dust as it warms along shock ridges and in inner rings near the centers. Radio arrays would scan for neutral hydrogen and molecular gas piling up in lanes, and they would rescan those same regions often enough to track growth and drift. None of that is done once. It is done again and again with careful calibration because the payoff comes from comparing one epoch to another and teasing out small changes. On the ground, there would be a second wave of response in the way data is handled. When the target fills the sky and evolves everywhere, the data rate is enormous. Archives would need to absorb images and spectra from many facilities every clear night, and to keep them useful, everything has to be cross-referenced and standardized. That means shared calibration fields, common formats for timing and pointing, and stable pipelines that convert raw data into maps the whole community can use. Teams that build surveys already do this, but the scale here is heavier. You can expect observatories to lean on cloud and high-performance computing centers and to automate the grunt work so that humans focus on interpretation. The trick is to keep the system open enough that anyone can test an idea against the same reference data, while also protecting fragile satellite links and ground networks from overload during busy nights. Artificial intelligence would earn its keep here, but not as a black box that decides what is true. It would be a triage system and a pattern finder. Models trained on past interacting galaxies could flag where tidal features should grow fastest, and anomaly detectors could point astronomers to regions where something did not follow expectations. In time domain work, Software could watch thousands of fields for new supernovae and transients and push alerts to telescopes that can zoom in for details. For the moving sky problem, machine learning tools could help separate the layered structures of our Milky Way from the newly nearby Andromeda features by recognizing textures and velocity patterns rather than by simple brightness thresholds. When jargon sneaks in, it just means this: computers do the sorting so that people can do the thinking. Citizen science would not sit on the sidelines. All sky cameras, the kind that already track meteors and auroras, could be networked to provide a global movie of the new panorama. Amateur astronomers with small telescopes and decent cameras can already reach astonishing depths by stacking short exposures. With guidance on targets and cadence, a distributed community could contribute real science. Data from that network would not replace professional work, but it would fill gaps in time and geography and add redundancy. Schools could host small spectrographs that record simple line shifts from star-forming regions, turning classroom labs into a global monitoring project. None of this requires expensive equipment. It requires coordination and simple standards. On the safety and infrastructure side, agencies would stay calm but make sensible upgrades. Satellite operators would turn up the dials on radiation monitors and error-correcting software because a slightly busier cosmic ray background translates to more bit flips in memory and more transient glitches in detectors. That is manageable with redundancy and algorithms that check and fix corrupted bits. Sensitive payloads might add a few millimeters of shielding around critical electronics in future designs. Deep space missions, the ones that travel beyond Earth's magnetic cocoon, would fold a little extra mass into their shelters and plan routes to minimize time spent in the highest particle fluxes. That is not glamorous, but it is practical, and it is the same kind of engineering judgment that already handles solar storms. Aviation authorities would tune procedures that are already on the books. High-latitude flights see more radiation from space simply because Earth's magnetic field opens toward the poles. Airlines sometimes shift altitudes or routes during strong solar events to keep doses well below recommended limits for crew. With a long-term uptick in the cosmic ray baseline, they would apply those standards a bit more often, guided by real-time monitors that track the particle rain through the atmosphere. None of this is new. It is an incremental extension of what is routine today. The power grid question lands in the same bucket. Geomagnetic storms that stress transformers and long lines are driven by the sun's eruptions and the way the solar wind's magnetic field couples to Earth's field. A galactic merger does not flip a switch on solar activity. Grid operators would stay focused on solar alerts, harden vulnerable nodes, and practice safe mode procedures for rare extreme storms. If anything, the cultural spillover from a spectacular sky might help sustain funding for space weather monitoring because the public's attention would be on the larger context of Earth's place in a changing cosmos. Early warning systems for rare but consequential events would get special attention. The prize here is a nearby supernova. You cannot prevent it, but a few hours' notice from neutrino detectors would let you watch the birth of the visible light curve from the first moment and gives aviation and satellite operators time to make minor adjustments. Neutrino detectors are big tanks of water or specialized materials that flash faintly when ghostly neutrinos pass through and occasionally interact. They are already running. Upgrades would expand their sensitivity and their ability to triangulate the direction of the source. A global network that shares triggers instantly would make the most of a rare event. Policy naturally follows the technology. The spectrum that radio astronomers use to map neutral hydrogen and molecules is crowded by commercial signals. Regulators would be under pressure to keep key windows clean or at least quieter during coordinated observing blocks. Because the science case is obvious and time-sensitive on human scales. Light pollution policy would get a nudge, not because the sky will wash out from the galaxy's glow, but because the new view invites people outside. Cities and parks may adopt better shielding and warmer-colored lighting that leaves the stars and the galactic structures more visible while still keeping streets safe. Satellite operators would be asked to keep reflectivity low and to share orbits so that wide-field images are not riddled with streaks. None of that is a ban on space commerce. It is a push for better coexistence when the sky has become a public resource in a fresh way. Science funding would shift in visible ways. Agencies would prioritize instruments that map motion, like precise astrometry missions, and instruments that track gas conditions, like wide-field radio and infrared surveys. They would also put weight behind a space-based gravitational wave observatory tuned to low frequencies, because the eventual dance of the central black holes is a once-per-civilization signal. Pulsar timing arrays, which time the blinks of dead stars with incredible precision to sense ripples in spacetime across the galaxy, would add and upgrade stations to sharpen their ears for the slow waves from a black hole pair in the making. These projects take years to build and decades to run, so starting early matters. Education would ride the wave. Planetariums would replace simulated skies with live data mosaics. High school and undergraduate courses would use current images of star-forming rings and tidal tails as lab material, teaching basic physics through nearby examples. Teams would build simple software that lets students measure velocities, identify shock fronts by their spectral fingerprints, and track how features evolve semester to semester. The big win is that the sky itself becomes the textbook. That tends to stick with people far more than abstract diagrams. Culture, in a broader sense, would respond too. You would see more people outside at night, and you would hear more questions in everyday conversations about what this arc or that patch is. Media would do a better job when experts work with them early to set expectations. Or without hype, hazards explained clearly and kept in proportion, and uncertainty communicated as a range with plans to narrow it. That kind of communication builds trust, which pays off later when rare events do happen and you need the public to listen and to act calmly. Global coordination is the unglamorous backbone. The sky crosses borders, so data needs to as well. The most effective approach is a standing set of agreements for open data with clear credit, rapid alert protocols for transients, and common standards for metadata so that one team's maps can be layered cleanly on another's. Time zone coverage matters. Telescopes in the south pick up what the north misses and vice versa. Funding for facilities in under-resourced regions is not charity. It is how you get full sky, around-the-clock coverage. The merger gives a concrete reason to make that investment. There would also be targeted mission concepts that make use of new vantage points. A small fleet of microsatellites could be placed at Earth-Sun Lagrange points to watch the sky in high-energy bands continuously, each with overlapping fields so that no transient is missed. A mid-infrared telescope placed in a Venus-like orbit could pick up warm dust signatures with less interference from Earth's own heat. A pair of small radio arrays on the far side of the Moon would offer a radio-quiet platform to image neutral hydrogen at wavelengths that are hard to access from the ground because of human interference. None of these require giant budgets. They require a clear science case and steady support. Planetary defense would quietly expand. Surveys that search for near-Earth objects would keep doing their work, and they would push deeper for long-period comets because the background rate could rise over geological time. A space-based infrared surveyor is particularly helpful here because it sees the heat from dark objects that are hard to spot in visible light. The operations side would test deflection techniques on harmless targets so that if a real threat appears someday, the playbook is proven. The merger does not force this. It makes the argument cleaner to maintain momentum on programs that are wise anyway. Medicine and public health have a minor role, but it is there. As aviation adjusts and as spaceflight ambitions grow, agencies would update exposure guidelines using fresh measurements of the high-altitude radiation field. Clinics that serve aircrew might add simple, cumulative dose tracking to routine occupational health records, the same way dosimeters are used for medical staff who work around X-ray machines. For the general public, the added dose at ground level would be small compared to natural variation with altitude and latitude, so this remains a workplace issue for specific groups, not a public health campaign. Insurance and economics are less obvious, but they play in. Satellite fleets carry risk from radiation-induced failures, and a slightly higher background nudges rates and design choices. Insurers will ask more detailed questions about error correction strategies and redundancy. Power companies will invest in better storm time procedures and hardware resilience, insurance or not, because a single poorly handled solar storm can cost far more than incremental upgrades. None of these responses tie directly to the merger as a trigger. They track back to a general recognition that space weather and cosmic weather are part of doing business in a spacefaring and networked world. Ethics and governance do not disappear just because the subject is astrophysics. Decisions about spectrum use, satellite reflectivity, and open data affect many stakeholders. The fair way to navigate is transparent trade-offs. If a satellite operator agrees to a darker design and to share orbit information to help astronomers avoid stray light, regulators can offer streamlined licensing. If radio quiet zones are established near major observatories, local communities should be at the table early to make sure their needs are met and that the benefits flow back in the form of jobs, education, and shared infrastructure. When the sky is a shared asset, shared responsibilities follow. You can also expect a few moonshots to be proposed. A telescope array that blankets a continent, a network of balloon-borne observatories that float for months above the weather, a deep ice neutrino detector upgrade, or an interplanetary relay to triangulate high-energy transients from different vantage points in the solar system. Most big ideas will be trimmed to what is feasible. A few will get green lights because the moment is perfect for them. The test is simple. Does the project return data that cannot be gathered any other way? And does it build capacity that will be useful long after the dramatic phases of the merger wind down? In the same breath, it is smart to put resources into long-term archives. Decades from now, someone will want to compare an image from the first clear night to one taken after the second close passage. That only works if the files are still readable, the calibration keys are preserved, and the documentation is clear. Investing in curation is not exciting, but it is the foundation of everything else when the science goal is to track slow change across generations. Finally, there is the personal layer. People will go outside more. Teachers will plan night excursions. Communities will designate darker parks. Camera makers will add simple sky tracking modes because demand rises. Amateur telescope makers will publish guides to capturing the overlap lanes and the faint tidal arcs. Backyard astrophotography will explode in popularity, and with it, a wider sense that the sky is not static. That cultural shift matters because it feeds science with volunteers, it supports funding with enthusiasm, and it keeps the conversation grounded when headlines drift toward exaggeration. So the human and scientific response is not a sprint or a scramble. It is a coordinated pivot. Observatories switch to all sky, repeated coverage, and share their data fast. Engineers harden satellites and keep airplanes safe with modest tweaks. policymakers protect the night and the radio spectrum without choking innovation. Educators and citizen scientists turn the new sky into a classroom and a lab. Big projects aimed at the central black holes and at the gas flows get a tailwind, while practical defenses against rare events are set up and connected. All of it flows from a calm reading of the situation, a once-in-civilization chance to watch galaxies reshape themselves, with hazards that are mostly modest and best handled by doing the basics well and doing them together. All that organization and steady watching are really about one thing: documenting how two structured spirals turn into one new home galaxy. When the long dance winds down, you are left with a remnant that astronomers like to nickname Milkdromeda. It is not a poetic flourish, it is a practical label for a system that will look and behave differently from either starting disk. The broad picture is simple. The elegant thin spiral patterns that used to dominate will be gone, replaced by a smoother, puffier body whose light gets brighter toward the center in a steady way rather than along arms. The orbits of most stars will be scrambled from tidy circles into a mix of directions, so the support against gravity is mainly random motion rather than organized spin. In that final state, the central black hole will be far larger than the one we live with today. Sagittarius, a star in the Milky Way, weighs about a few million suns, and Andromeda's black hole is well over 100 million suns. Add growth from accretion and from the final merger of the pair, and the core of Milkdromeda will host a single giant black hole that is comfortably in the hundreds of millions of solar masses, possibly more if gas fueling during the merger was efficient. That object will not be a constant lighthouse. It will have active spells when fresh gas finds its way in, lighting up an accretion disk and maybe launching jets, and quiet spells when the pantry is empty and the nucleus glows only faintly. Over long stretches after the gas reservoir thins, quiet will dominate. The stellar body will settle into a shape that is close to spheroidal, not a perfect sphere but rounder than any thin disk. If you could slice it in half and map the stars, you would see a smooth profile that brightens steadily as you walk toward the center. Dynamical relaxation, which is just the system rebalancing itself as the gravity field changes rapidly during the encounter, leaves stars on orbits that loop in many directions and cross one another. That is why the sharp spiral edges fade. The level of rotation left over does not drop to zero. Remnants can keep a gentle spin, often noticeable as a slow twist in the way light and motion align near the center. But the headline is random motion, not rotation. The gas situation is equally important. In the gas-rich phases of the encounter, shocks and bars feed starbursts and outflows. After that, most of the cold gas that could easily make stars is either consumed or heated. The leftover atmosphere around Milkdromeda is a hot corona that extends far beyond the visible light, at temperatures of many millions of degrees. That halo glows in X-rays and cools only slowly. It is not a good fuel source for large-scale new star formation, because cooling from those temperatures takes a long time unless something compresses the gas locally. That is why massive merger remnants tend to end up redder and quieter, with star formation tapering to a low simmer. Even a quiet remnant has structure to enjoy. The faint outskirts will be laced with shells, loops, and streams, fossil traces of earlier passages, and of small satellite galaxies that were stretched out and absorbed. These features are low contrast, but they persist for billions of years because the outer gravitational field is gentle and phase mixing. The process that smooths out substructure is slow out there. Globular clusters will be sprinkled across the halo in large numbers. Many will be the same clusters we know now, grown older and redder. Some will be younger, born during the starburst peaks when dense gas clouds in the overlap zones collapsed into massive bound swarms of stars. Those new globulars tend to be metal-rich compared to ancient ones because they formed from gas that had already been enriched by previous generations of stars. The stellar population overall will drift toward older ages. The bursts during the merger add fresh cohorts, but once the gas is used up and heated, the assembly line slows dramatically. Over a few billions of years, the light becomes dominated by longer-lived, cooler stars. If you are used to a sky full of blue star-forming knots and bright emission nebulae, that palette fades. In its place, you get a calmer backdrop where the central glow is smooth and the standouts are compact star clusters, the occasional planetary nebula, and the faint tracery of tidal leftovers that long exposures will still reveal. Triangulum, the smaller spiral that orbits Andromeda today, is very likely to be part of the story as well. It may be dragged into the merger during one of the late stages or be swallowed not long after. When it arrives, it contributes stars, clusters, and some gas, but by then the central dynamics of Milkdromeda are set. Triangulum's material will add asymmetric ripples and fresh shells in the outskirts, and if any remaining cold gas survives the trip, it can spark local star formation for a while in streaks and knots before being heated by the surrounding environment. Over the very long term, most of the local group's dwarfs will be cannibalized the same way, each one leaving a faint signature that careful mapping can follow. From a world orbiting a star within the final remnant, the night sky depends a lot on where you are in that new structure. If you live in the outer halo, far from the center, the sky is sparse and quiet. The central glow is a distant, smooth ellipse of light that changes slowly with your orbit. You would see many globular clusters as tiny, concentrated pinpricks, and with decent instruments, you could trace long arcs of tidal light that mark where dwarf galaxies were peeled apart. Bright, blue, short-lived stars are rare in your neighborhood, so nearby supernovae are uncommon. It is a stable view, not dramatic night to night, but rich in detail for patient observers. If you live in what remains of a thickened disk or in the inner halo, the central glow is larger and the density of background stars is higher. Bright star-forming regions are scarce compared to the early merger epoch, but they are not absent. Minor accretions and leftover dense gas can still make pockets where new stars light up for a time, and those pockets stand out sharply against the older starlight. You might also see wispy dust lanes orbiting near the core, leftovers of gas that has not yet been heated all the way or new material that fell in along a filament. Those lanes would be less prominent than the grand dust bands of a classic spiral, but they add texture to the central light. Closer to the center, life becomes more complicated and, for many forms of biology, less comfortable. The density of stars climbs, and the rate of interactions and transients is higher. The central black hole has occasional active spells if gas is available. Those spells are mostly hidden behind dust if you sit in the plane, but radiation leaks out along the poles. Planets hanging out within a few thousand light-years of a long active nucleus would see a higher background of high-energy photons for extended periods. If you go closer still, within a few tens of light-years of the core, the environment includes frequent supernovae and blinding clusters of massive stars, which is not friendly to atmospheres or stable climates. Those inner zones are interesting for astrophysics and harsh for habitability. The solar system's ultimate fate inside Milkdromeda splits from the galaxy's general story. Because our star has its own clock, the Sun will exhaust its core hydrogen in roughly a few billions of years from now, swell into a red giant, and shed its outer layers, leaving behind a white dwarf. That transition unfolds largely irrespective of whether the remnant has fully settled. If the Sun remains bound to Milkdromeda, its white dwarf will orbit for untold trillions of years, cooling slowly. If the Sun is scattered into the outer halo or ejected outright as a hypervelocity star during some extreme interaction, the white dwarf will do the same, drifting in a much sparser environment. In either case, the neighborhood long after the merger will be dominated by old dim stars, brown dwarfs, white dwarfs, and the rare bright interlopers from smaller, late-forming pockets of star formation. Dynamically, Andromeda will spin down its drama and enter a maintenance phase. The outer halo will keep swallowing small dwarfs that wander too close, each one kicked around by tides until it dissolves. The central black hole will have quiet centuries punctuated by flares when a cloud strays in or a lone star gets disrupted by tides. Those flares brighten and fade over months to years, hardly changing the overall appearance of the galaxy to human eyes, but adding entries to catalogues and keeping high-energy astronomers entertained. The globular cluster system will evolve as clusters slowly sink via dynamical friction, which is a small gravitational drag that acts over very long times. Some clusters will be shredded by tides near the center, others will cruise untouched for ages in the halo. The chemical makeup of Andromeda will carry scars from its past. The inner regions, where gas once pooled and star formation was most intense, will be metal-rich, which means stars with high abundances of heavy elements. The outer halo will host a mix, including ancient metal-poor stars from the original halos and strands of more metal-rich stars that were yanked from the disks and from dwarf galaxies. The gradient from rich to poor will be smoother than in today's Milky Way because radial mixing during the merger blends material across large distances. That mixing shows up in stellar archaeology surveys that analyze the fingerprints of different elements in stellar atmospheres. In the remnant, you would find a wide spread at a given radius rather than a neat gradient. The dark matter halo, the invisible mass that envelops the whole system, will be larger and deeper than either progenitor's halo. The way it responds to the changing distribution of stars and gas during the merger leaves a structure that may be less cuspy in the very center than a naive model would predict, because energy pumped into the inner halo by bars and by repeated inflows and outflows can soften the central density slightly. That detail matters for theorists and for interpreting the orbits of stars near the center. For anyone living out in the galaxy, it simply means the overall gravity field is steady and deep, holding on to streams and shells for a very long time. If you wonder about the broader cosmic neighborhood, the local group becomes a one-galaxy town surrounded by a handful of stragglers. The space beyond is expanding, and on the tens of billions of year timescale, galaxies not gravitationally bound to us drift farther away. That has little day-to-day effect on life inside Andromeda. It does change the supply of new infalling dwarfs over long times, thinning the stream of fresh accretions. Eventually, Andromeda lives mostly on its own leftovers, recycling gas that cools out of the hot halo and nibbling on the last few companions that remained nearby. From the standpoint of observational astronomy, the far future view from inside the remnant has trade-offs. You lose the grand, edge-on spiral of the Milky Way and the majestic face of Andromeda filling a big swath of the sky. In exchange, you can study the fossil record of a merger up close. Shells, streams, and globular cluster distributions become a homework set you can work on with modest telescopes. The central black hole's occasional flickers provide natural experiments in accretion physics at a comfortable distance. And because the remnant's light is smooth, deviations stand out clearly, making it easier to find the rare pockets of fresh star formation or the ripples from a newly ingested dwarf. For habitability, the message in the long run is that the galactic environment calms down after the dusty fireworks of the merger years. The background of radiation in the outskirts is lower than during the starburst peak. The rate of nearby supernovae falls, The hazards for a planetary biosphere return to being dominated by local conditions: the type of star, the stability of its planet's orbits, the protection from its magnetic field and atmosphere. Civilizations that plan across long times might even choose their addresses accordingly, preferring wide, low-density orbits in the outer halo to minimize exposure to bursts and to keep sky glow down, or choosing orbits nearer the middle if they want bright skies and rich cluster fields for observation. One practical detail worth mentioning is the baseline sky brightness from the remnant's smooth glow. In the outer regions, it is faint, like a thin smear of light that you notice only from very dark places. In the inner regions, it raises the floor of the night a little, much as being near the current Milky Way's central bulge would. That is not enough to change ecosystems or to erase the starry sky. It is an aesthetic change that nature parks and observatories will account for by placing themselves in the right locations and by continuing to preserve dark skies from local light pollution, which remains the dominant factor for visibility. As for measuring the final parameters of Andromeda, future surveys would pin down the total mass, the shape of the dark halo, the size of the central core in the stellar light, and the exact mass of the central black hole. They would do that with many of the same tools used today: tracking the motions of stars, mapping hot gas in X-rays, weighing globular clusters by their orbits, and timing variable sources. The answers would be numbers with error bars, not slogans, and they would reflect a system whose history is written in long arcs across the sky and in the chemistry locked into stars. There is no need to romanticize the endpoint to appreciate it. A big, redder, more spheroidal galaxy is not a downgrade. It is the normal outcome of gravity working on large scales with the materials at hand. It brings a different kind of beauty and a quieter setting for worlds in its outskirts. If you could walk that future night and look up, you would not see grand arms, but you would see a deep, smooth glow with filigree details that tell a very long story. You would know that the black hole in the middle grew from a pairing of two, that the globulars you spot are survivors of old disks and children of later bursts, and that the faint curls far off are the long memory of galaxies that wandered in and left their outlines behind. And you would live with the practical comfort that, after the upheaval, the galaxy around you has settled into a stable shape that changes only slowly, leaving the day-to-day fortunes of life to the local star and the close companions that orbit it.